Descent Energy Management course. Today we are talking about how to manage the aircraft energy through the descent. A challenging exercise for all pilots, including experienced one. My experience as line training captain shows that one of the main reasons of failure at commander grade is the mismanagement of the aircraft energy. Well, I found in an old folder a course that I used to give many years ago to cadet pilots joining a company as first officer. This course is designed to be delivered more or less halfway through the line training in order to give them a number of tools and required knowledge in order to manage the aircraft energy. Turns out that there is no regulatory requirement to give any such course. There are little bits of energy management information provided during training, but a full training, as I just said, is not required. And my course remained forgotten somewhere in the folders of my computer. Well, today I'm going to reveal to you what are the contents and what are the recommendations and rules that are given to pilots that needs to manage the aircraft energy through the descent. If you're interested in this topic, follow me into the pilot lounge. Ladies and gentlemen, very welcome again, and today we are discussing about managing the aircraft energy into descent. Descent management course was a course that was done in the past. Today it's not exist anymore, but you might still be interested in what is contained in this course. Now, before starting, I shall remind you that there is a video disclaimer to all my video. I will be very grateful if you're familiar with what is said on the disclaimer. Again, I will be very grateful if you could consider like and subscribe to my channel and share this video with your fellow colleagues. So I'll put my hands forward. This video is going to attract a lot of dislike because it has a very limited audience. So please do not watch this video if you're not interested, and most likely the majority of the pilots are not interested. Managing the aircraft energy into descent is a very challenging exercise, but you get exposed to this exercise only once you are in the line training. So if you are a TPL student, well, I would say it's a bit too early to discuss this. Even if you start in the line training, is a bit too early. The right moment to look at this course is between 40 and 80 sectors through your line training while joining the company. So this is the people for who this course has been designed. If you are an experienced pilot, most likely this video is totally useless to you. So, well, you might, if you're curious, you can give a look to it, but you might find it, I would say, redundant or talking about things that you already know. But if you are going for commander grade, then this video might be very useful to you once again. It's gonna be extremely boring in that case because you already know all the contents, as I just said. But you might take it, my suggestion is that you sit down, relax, look at this video and take it as a very boring chat with an old pilot who's trying to help a fellow young colleague in becoming captain. What we've been talking today is things that a professional pilot should know. So it's all things that you know, but we're gonna try to pinpoint a number of elements that are extremely important in the mind of a pilot in order to understand how to manage the aircraft energy. And in fact, managing the aircraft energy into the descent remains a very challenging exercise. It will be challenging during your line training as an airline pilot, and it will remain in some cases challenging even during your line training as a captain. And that's why I'm saying you should look at this if you're going for commander grade, because in my personal experience during command grades, one of the major reasons of failure has been mismanagement of the aircraft energy. So managing the aircraft energy is a challenging exercise, remains a challenging exercise. So, well, let's move forward and let's try to pinpoint a little bit of those information that we have to look at in order to correctly manage the descent of the aircraft. Now, one important thing is that this course was designed specifically for the 737NG. Now, because of very similar performance, this is absolutely applicable to the 737 MAX. But of course, if you're flying different type of aircraft, the numbers we're going to discuss are going to be different. So you have to re-elaborate these numbers to see if they actually apply to your aircraft, okay?
Paolo's Pilot Lounge. Like and subscribe now.
First of all, well, let's start with a very simple concept. What is the objective of the descent? Well, to transition from the cruise phase to the approach phase in a safe and efficient manner. That's quite obvious. But what is safe? Well, obviously the safe means respect of all aircraft limitation. Respect the speed. Don't overspeed the flaps when you start configuring, for example. And at the same time, respect all the minimum route altitude, minimum off-route, minimum grid altitude, MSAs and so on. Respect of all minimum altitudes. An additional thing will be to make an ideal descent in order to minimize the fuel waste. Today there is a lot of attention to ecology, so saving fuel saves the nature, but most importantly, once we are in flight, saving fuel increases the amount of fuel we have available on board in case we need to take a diversion for an unforeseen circumstances. And this is very important, so we want to save fuel throughout our descent. In few words, I'm saying, know your aircraft. Know what is the performance of your aircraft, and know how to handle your aircraft. That's what a professional pilot should be able to do, and I would say it's pretty obvious. Now, the handling, we're not really going to be discussing on this video. So, what is efficient? Well, obviously, the most efficient thing to do is to fly the economy speed of your company. So you insert a cost index in the FMS will return to your speed, flying the FMC speed, and anyway, staying as close as possible to the economy speed is going to be the most efficient way to fly. Of course, this reduces the fuel burn. Actually, this reduces the total cost of operation in the company. And another thing, that if you reduce the flight time, you actually reduce the time the engine is running, and you actually reduce the time the fuel is being burned. So if the company will plan a flight for you with a standard arrival route and so on, of course, if you can manage to have shorter flight time through your experience, through asking for direct, for example, well, you shorten the flight time, you save fuel, you are more efficient. And of course, to reduce the stress to the aircraft components. Now, this sounds stupid, but having as a habit to extend the flap at the maximum design speed for the flap extension will increase the stress to the aircraft components. For example, on the 737NG, it is not recommended by Boeing. On the training manual, it says there is no recommendation to use speed brakes and flaps at the same time, but this is not prohibited. Now, here I'm touching a hot topic, for example, because I know very well that there is one of the major 737 operator company that actually encourage his pilots to use flaps and speed brakes together. Well, you have to adapt to company policy. Obviously, the maintenance program will be sized and designed for that. But remains the fact that ideally try to stress the least all the aircraft components. So using the lowest drag as possible to make your descent most efficient and to stress as little as possible the aircraft components. Now, what is the ideal profile of the descent? In these slides, obviously, well, here we're talking of something which is absolutely obvious, but of course we have to go through these obvious things. And what is the ideal profile of the descent? Well, because the engines are most efficient at high altitude, the engines are designed to be efficient at a thrust setting of approximately 90-95%. Once we are in cruise at our altitude, our engines are running at very high regime because of the lower air density. But this means that the engine is running at the highest efficiency. If we fly at lower altitude, yes, we will get high efficiency on the engine at 95%, but that will be a massive amount of thrust that could be only used to climb. And because we are in the descent, we don't need that much thrust. If we want to use an engine at a thrust setting of 60%, is going to be significantly more fuel consuming as compared to the actual increase of thrust we obtain. So maybe to go from idle to 60%, we might need to give twice as much as fuel, but we don't get twice as much as thrust. So that's why, ideally, we want to use the thrust in cruise, reach the top of the descent, and start our descent at the economy speed with thrust idle. And ideally speaking, we would like to keep the thrust idle until few seconds prior landing. So you see that we do our economy descent. In this example, I took 270 knots, and which is the speed calculated by the FMS. The FMC normally can calculate also the top of the descent. So ideally, in a perfect world, I would start descending with the calculated FMS. Now here we're touching a hot topic, because the FMS can calculate the profile. So this profile that you see in the slide can be calculated by the FMS. But what happens is that when I started flying, the FMSs were fairly unreliable. I would say once over twice, the FMS profile was totally whatever, crap, unreliable, unusable. So pilots really had to be careful about what was the FMC profile, about cross-checking the FMS. Nowadays, the situation is getting worse, because I would say the FMS start to be pretty accurate and well programmed. So if you insert the correct data in the FMS, well, modern FMSs can give you a fairly reliable profile, which means that probably 20 times out of 21, the FMC profile is correct, and this brings the pilot in the false belief that the FMC is always correct, which that is not the case. So make sure that you always cross-check the FMS, because the fact that the precision of the FMS has increased in time and its reliability is increased does not mean that that instrument is 100% correct. So make sure that the FMS is properly programmed, first of all. And even if it's properly programmed, because it's a complex computer, there are many reasons, millions of reasons, why the FMS could give you an incorrect profile. And you should always be backing up the FMS profile with your own calculation. This is one of the reasons of failure: blindly believing the FMS without backing up the calculation. Well, let's get back to our descent profile. You see that we say top of descent, we start descending 220 knots. We reach the first deceleration point where, with more or less of a rate of 500 feet per minute, the FMC will give you a continuous steady deceleration down to the speed limit of 250 knots below level 100, which is normally inserted in the FMS because that's ICAO speed restriction, unless removed by ATC in airspace Alpha Bravo Charlie. We continue to descend 250 knots, and then we reach the point decel number 2, the second deceleration, where from 250 knots with a rate a bit slower, from more or less 200 feet per minute, the aircraft starts decelerating, reach the flap configuration speed. At this point, there is an initiation of final constant descent angle. Of course, through this deceleration, there is configuration of the aircraft, and once we are on 3 degrees, we have the final configuration of the aircraft, and finally, more or less 4 nautical miles final, we should have the spool up of the engine. So we start adding thrust again, because that is needed for the approach. So this profile that you see here is more or less what the FMS calculates. I want to attract your attention on this 200 feet per minute deceleration segment, because that's where very often pilots make mistakes. When the FMC decides to decelerate, if you are following the FMC profile, you have to do what the FMC tells you. In that segment, very often I see pilots adding thrust because they say, well, we are decelerating too much. They interpret it as a mistake of the FMS that give you a too early deceleration. Well, that's wrong. If the FMS calculated that that is the deceleration point, and if you are following the FMS profile, if you are descending below, that is not a problem. But if you are following that FMS profile, well, you have to start configuring the aircraft correctly, because you see the next point is going to be the start of the final approach segment with the constant descent angle, which is the angle to which the final approach segment has been designed. So the FMS takes the final descent angle starting from the runway, draw a line, and brings you to this initiation of final constant descent angle point. I'll come back to this point because this point, I very often call it the mystery point. So there is a lot of interest in managing the approach considering this mystery point. So I'll come back to this later on. Alright, having defined what are the objective of a descent, let's get into the detail of what is the aim of our course in order to learn how to achieve those objectives. So first of all, we have to understand a very basic concept, which is always known by the pilots. I would be very surprised if you are a pilot and you don't know this concept, and this is the concept of the altitude by 3. We then have to understand the aircraft energy. Again, this is a concept that should be known by all pilots. Then we have to understand the logic of the VNAV, because modern aircraft like the 737NG, they do use VNAV, and the pilot is using the FMS for the management of the descent. So we cannot say, okay, I just managed the descent that this was done on old-fashioned aircraft just based by distance. You will have to use the VNAV. The FMS might give you a number of help, and we have to learn how to use it, because as I said, it's very useful, but sometimes it might be misleading. Finally, we have to discuss the cases where the VNAV is unavailable. And there are cases where these happen. I had several cases of VNAV unavailable, pilots being aware of this unavailability of the VNAV, despite still making the mistake of using the FMS, and screw up the profile because they were trusting a profile that they knew was incorrect. So, well, let's start with the first step and the altitude by 3. The altitude by 3 concept is very simple. You should know very well that an aircraft, in order to lose 1,000 feet, needs 3 nautical miles. So that's the altitude by 3. 1,000 feet multiplied 3 makes 3 nautical miles. Which means that, for example, if I'm at 40,000 feet, how many nautical miles do I need to land? How far away should be ideally the runway? If I'm flying at 40,000 feet, well, altitude by 3, so 120 nautical miles. If I am at 30,000 feet, what should be the distance of the runway? Obviously, altitude by 3, so we are talking of 90 nautical miles. If I am at 20,000 feet, the runway should be at 60 nautical miles from me. And if I am 10,000 feet, altitude by 3, so we should be at 30 nautical miles. 5,000 feet. Color is switching in orange here, and I say 15 nautical miles. I'll come back to this changing color in a moment. And 3,000 feet, that should be more or less 10 nautical miles. If we want to be precise, we should say 9 nautical miles, okay? But I'll call it 10 nautical miles. But you see that at this stage, I start asking myself a question. Okay, but 10,000 feet. That is the altitude at which the aircraft reduced the speed from 280 to 250 knots. So should it be 30 nautical miles at 250, or should it be at 280 knots? And the same thing at 15 nautical miles. Should I be at 250 or at 200 knots? Because that's more or less the point where aircraft start decelerating, configuring for the approach. So yeah, we have to answer to this question. We have to take into consideration the deceleration. So now, the reason why I change color in this 15 and 10 nautical miles, you see orange and red, it's because of a factual problem that we will discuss in a moment. And this factual problem is that in the descent planning, once you are, I would say, more than 20 nautical miles out, so 10,000 feet, 30 nautical miles, you have, I would say, a wide margin of control on the track mile. So, of course, the ATC will give you the direct routings, will give you the routings. You don't really know what the track miles are. but you do have margin to correct the profile. You can adjust the speed according to the fact that you're high or low. Once you start being 20 nautical miles or less, I would say within 20 nautical miles, well, the games are done. Normally, once you are 15 nautical miles, it's evident what's going to be the ATC plan to close you for the final. Is there going to be delays, long vectors? Is there going to be a direct routing? Very often, I would say 80% of the times, once you are 20 nautical miles from the threshold, you very well know, you can exactly determine how many miles you are missing from the threshold. In many cases, the ATC will tell you if the vectoring is a bit doubtful and you don't really know. You can't really know what the mileage is, but in all cases, the closer you get to the runway, the more clear is, what's the distance. So if I am on a vector to intercept, I know very well that the air traffic control might close me a little bit towards the final approach fix, or maybe it might turn me a little bit outside and give me a bit more track miles to build up more distance with the preceding traffic. But as a matter of fact, once I am on the final vectors toward the runway and I see 18 nautical miles, well, it could be a bit shorter, 15 nautical miles, could be a bit longer, 20 nautical miles, but there's no much space to play with, so I know exactly what the distance is. So when I'm far away, I reason stem altitude, what should be my distance. When I'm close to the airport, I reason in term, what is my distance, what should be my altitude. Because once we are within the 20 nautical miles, it's very important that you reason on the profile. You must bring your aircraft on the correct profile. You cannot accept having your aircraft high on profile. You can fix the problem of the speed, but you can't very often fix the problem of the profile. The profile has very little margin of error. So you must bring your aircraft on the profile. Once you are within 20 nautical miles, my reasoning is the other way around. We're 15 nautical miles, what should be my altitude? What is my altitude now? What should be my altitude, okay? So in the altitude by 3, there was this question that we have to answer. And the question is, okay, but 10,000 feet should be 300 knots to 50 knots. Is there any difference? Yes, there is difference. On the 737NG and a high performance aircraft, which are very performance, very efficient wing, what happens is that you must absolutely take into consideration the deceleration of the aircraft. So it means that we call it altitude by 3 plus deceleration. So you do altitude by 3 with 10,000 feet, so 30 nautical miles, but if we show up at 300 knots, we have to decelerate at 250 knots, you see, and doing deceleration. The rule for deceleration is 1 nautical miles equal 10 knots. So here we're getting some rule of thumbs that we have to, I would say, put in the pocket. Let's keep it as a golden rule to bring into the pocket. So the aircraft energy, 1,000 feet of energy corresponds to 3 nautical miles. So an aircraft, which is 1,000 feet high, can glide for 3 nautical miles. And an aircraft which is 10 knots faster can fly straight level without thrust for 1 nautical miles. You see, we can start doing some math there, because we can say that 30 knots corresponds to the energy of 1,000 feet. If I want to fly at 200 knots and I find myself at 230 knots, I have to fly straight and level without losing altitude for 3 nautical miles. And if I want to descend by 1,000 feet and maintain the speed of 200 knots, well, I have to fly 3 nautical miles thrust idle. So whether I would be losing 1,000 feet, whether I would be losing 30 knots, that will be exactly the same effect, flying 3 nautical miles of distance with the engine at idle thrust.
Paolo's Pilot Lounge. Like and subscribe now.
Let's take in this example. I've set a cost index 6, and which gives us 245 knots. Okay, let's take in this example for the aircraft does not have the deceleration at 10,000 feet, because the 10,000 feet is 250 knots below level 100. So we're 20,000 feet, we are at economy speed. The only deceleration is going to be the deceleration for the start of the aircraft configuration. Okay, so again, we're 20,000 feet. The question is, what should be our distance? Well, I think you got the game. 60 nautical miles, altitude by 3. Okay, we find ourselves 5,000 feet, 245 knots, and you see that this is the beginning of that ramp of deceleration that will bring the aircraft into configuration. So what should be the distance? As we said, ideally, although the 737 can extend flap at 250 knots, we're not going to extend flaps at 250 knots. We ideally going to extend flaps at the maneuvering speed or something which is no more than 10 knots above the maneuvering speed. I say it's not prohibited. You could go flap one straight away at 245 knots, but that is not efficient. Okay, so in our ideal deceleration, now we find ourselves 5,000 feet. What should be the distance from the threshold? Well, altitude by 3 would say 15 nautical miles. But because I am at 240 knots and I want to start configuring, let's say ideally extending flap 1 at 210, 205 knots, let's make it easy, call it 40 knots deceleration, I have to consider that I have to lose this 40 knots in clean configuration. Of course, if I need more drag, as I said, it's not prohibited to use a speed brake, not prohibited to go flap 5. I could go flap 5 in speed brake if I need, but as I said, that wouldn't be efficient. So in this case, the answer will be 19 nautical miles. You see, I do altitude by 3, which is 15 multiplied 3, give me 15 nautical miles plus 4 nautical miles of deceleration. I need 19 nautical miles of distance for the ideal deceleration. So that is my ideal position for the descent. Okay, you see now I find in myself at 200 knots with flaps 1, probably starting the beginning of the final descent at that point that before I called the mystery point. And again, I'll come back to this mystery point again. The aircraft has to start the descent on a constant angle descent, probably 3 degrees descent. Okay, and what should be my altitude? Well, if I am 200 knots, flap extended, and 12 nautical miles, and you see what I was saying before. Now I'm reasoning the other way around, I'm not looking at the altitude and say what should be my distance. I'm looking at the distance I have to run, because if I'm 12 nautical miles, there's no doubt, now the game is done. The ATC cannot give me many vectoring. You know, maybe it's 11 nautical miles because they give me a little bit shorter vectoring, but there's no many games there to play. I know exactly it's 12 nautical miles. So I start from the distance, I am at 12 nautical miles. What should be my altitude? Which is the altitude that multiplied by 3 give me 12? Well, is 4. So 4,000 feet should be my altitude, because 4 by 3 give me 12. This is what I use for the approach. So for example, now I'm going down in the final approach segment, find myself 190 knots with flap 5, slat extended, of course, find 9 nautical miles. Again, I should be 3,000 feet. That is the correct profile for the ILS. And in fact, when I find myself at 3 nautical miles, what should be my altitude? Again, I should be at 1,000 feet. And you see that with the configuration, with increased drag, I should be able to make a continuous deceleration of the aircraft. Now, before we go any further, I want to emphasize a little bit the angle of descent on this profile that we just saw, because when you program the FMS will work in descent angle. So the FMS reasons in descent, in constant descent angle. So while for the first officer I would say we can put this on a second plan, for a captain I would say let's emphasize those descent angle, because this is very important. It probably happened to you a few times as an experienced first officer that sometime the captain knocked on your shoulder and say, I think we're getting a bit high, when you didn't realize or you didn't thought that you were actually high. Now sometimes that's very easy in that case, because when the captain prompts the first officer to increase the drag or increase the rate of descent, the first officers normally are very proactive. It's very unlikely, I would say it would be even unprofessional, if a captain would say, I think we should increase the configuration, should descend a bit more, and the first officer say, no, we're okay. I wouldn't believe my eyes, honestly, although I've seen something similar, but I deem it as very unprofessional. But when you become captain, it's going to be you, the man knocking on the shoulder of the first officer saying, hey man, I think we're getting high. And how can you determine that? How can you use the FMS to help you in doing that? Well, knowing the descent angle of the aircraft. A very important thing is to know that the 737NG has a descent angle in clean configuration, which is more or less of 2.7, 2.8 degrees. This flight path angle can be clearly seen in the FMC descent page. So if you want to familiarize with your aircraft because you're flying a different model, just go in the descent page and look at the flight path angle, and you will see the exact angle of your aircraft while descending idle. As I said, on the 737 MAX 737NG, you'll find yourself descending around 2.8 degrees in clean configuration. And that's a very important information, because this means that if the standard approach is of 3 degrees and your aircraft is descending clean configuration 2.8 degrees, this means that if you find yourself in clean configuration on a 3 degrees glide slope, well, you're already too high. You have to intercept the ILS from below, and you have to intercept the ILS or the 3 degrees glide path with a configured aircraft, because if you don't have at least flap 1, the aircraft will not have enough drag to be descending with 3 degrees. So the 2.8 degrees, it's the normal clean configuration descent. You will see, as I say, 200 feet per minute deceleration more or less, resulting in a very smooth descent angle. This platform of deceleration is something which is in the range of 0.5, 0.7 flight path angle. Okay, and these allow the aircraft to decelerate and configure the aircraft. And of course, the final segment is the 3 degrees or whatever is the angle for which the approach has been designed. So bear in mind these numbers, because this confirms to you that the aircraft is descending correctly. You can compare the actual flight path angle with the normal values that you are in the habit of seeing from your aircraft, and you might determine whether you're descending correctly or not. Sometimes, even on the 737, I see pilots that they find themselves on the glide slope, on the 3 degrees glide, clean configuration, they don't do anything at all, unaware of the fact that their aircraft is able to descend with 2.8 degrees and not 3 degrees on a glide slope. So it means that the aircraft will slowly accelerate through the glide. Alright, let's now apply this altitude by 3 comp set to a normal approach. Here I have an approach in Ciampino, which is my home airport, so I'm very familiar with that. And you can see that we have an arrival that comes from point Valma, going through a couple of VOR, which is Oscar Sierra Tango and then Choi My Papa. And then we go to a former NDB, which was URB Airport, today named LOCRI Point. And we go for the approach. So that's what is loaded in the FMS. Of course, the FMS will do the calculation and will calculate the top of the descent. So you see that here I got flight level 360, so altitude by 3 will give me what the top of the descent is, which gives me something like 9 plus 18, 108 nautical miles, I would say. Okay, so you see 360, but that's my calculation. 360 by 3, 180 nautical miles. Then I take the distance that I have from the chart, and I work out 108 nautical miles of route to calculate the top of the descent. So you see, it turns out that 31 nautical miles before the point Valma, I have to start my descent. And that's more or less the calculation that the FMS will do. It will do it in a more accurate way because it will take into account the weight of the aircraft, the winds aloft, and a number of other factors, economy, speed, of course, a number of other factors to have a better profile calculation. But the result of the FMS should be consistent with this number. Again, if I don't see something which looks like 30 nautical miles before Valma, I start having some doubts. I might allow a little bit of error. I might allow my first officer to follow the VNAV, even if the VNAV says, like, for example, 15 nautical miles before Valma. But let's say that the FMS doesn't want to start descent, just want to start after Valma, the descent, but start talking of 30 nautical miles. 30 nautical miles is 10,000 feet altitude. not very happy. I would probably say to the first officer, you know what, let's start this descent a bit early today. I don't really like what's in the box. There must be something strange, okay? Now, in an ideal world, on a theoretical world, what would happen is that, I start the descent and I fly my ideal profile as calculated by the FMS and as we saw in the beginning of the course, talking about objectives, okay? Now, as I fly, I reach the point Valma. Of course, I started my descent. It says I'm flight level 260, okay? So what is my current position? Am I high or am I low? Well, I lost 30 miles. I lost 10,000 feet. So it looks like I'm okay, but I could do the calculation again using the remaining distances. And if I do the remaining distances, I should do 40 plus 15 plus 12 plus 10 and 260 multiplied by 3 and compare with that distance, which is consistently correct. Now, what happens is that as I approach Oscar Sierra Tango VOR, I find myself at DME 12 and the air traffic controls pop up saying something that happens quite often if you're lucky, because there's no traffic, and they say, okay, fly direct to point LOCRI and clear for the ILS runway 15. And now you see that there is a problem that come up, because we were 12 nautical miles from Oscar Sierra Tango, we had another 15 and another 12 nautical miles to run to LOCRI. And now what happens is that if we fly direct to LOCRI, we just have 22 nautical miles, okay? We just cut out something which looks like 15 to 20 nautical miles of distance. And now we find ourselves high because we didn't consider the need of descending that much. And that's the point where things start going wrong. As you see in the picture, that's something that few times I see it happening in the flight deck. Very often the captain will take over controls or give some hints to the first officer and say, okay, let the automation do this or that. But if it's a common grade, it will most likely result in the fact that I would be telling you, well, you know what, I think you might need a bit more time, maybe another 6 months on the right-hand seat, familiarizing with aircraft energy and procedures, because this pilot in this picture is holding thrust lever closed and pulling the speed brakes. So he's using two hands, one for the speed brake, one for the thrust lever closed, meaning that is losing the management of the automation. The automation wants to give thrust. He realizes he wants to keep the thrust down, but is getting behind the aircraft with the management of the profile. So this could be a failure indeed. Your descent plan has failed.
Paolo's Pilot Lounge. Like and subscribe now.
So, how can we prevent this from happening? Well, it's very simple. When I program the FMS, I should take into consideration the possibility of a direct. So, once I am approaching top of the descent, I should take into consideration the possibility that the air traffic control give me a direct to Charlie Mike Papa to fly the approach, and give me a direct to Oscar Sierra Tango and then fly the approach. In both cases, because the distance between Oscar Sierra Tango and LOCRI is more or less 12 nautical miles, in both cases I would find myself over one of those two VORs with 22 nautical miles to run. So if I do my calculation, 22 nautical miles to run, it's more or less 6,000 feet, okay, because 6 by 3 is 18 nautical miles, but we'll need the deceleration for the configuration of the aircraft, which is another 4 nautical miles. So 18 plus 4 makes 22 exactly. 6,000 feet looks like working fairly well. This is not an accurate, precise calculation. If you would tell me 5,500 or 6,000, 7,000 feet, I would be happy as well, okay? But I would say 6,000 feet looks like in the math, corresponding well to our numbers. So what I can do is that I insert in the FMS 6,000 feet as a steady altitude on both points, so that the FMS will be calculating a profile that makes me cross those points at 6,000 feet and makes me ready for the routing in case the air traffic control gave me. Now, obviously, with the experience comes the fact that you will be able to determine whether the current situation will likely grant direct routing or not. If you hear dozens of aircraft with destination Rome Ciampino, it's very unlikely that you're going to get direct, so it is quite useless to descend that much and be on a profile which is capable of accepting a direct, because if there are delays, probably it's better to stay higher, and you could even expect to join a holding. So, you know, it's better to keep the altitude, and I would say taking the chance of being high in the rare event you get a direct routing. But as I said, with experience, you will build up the certainty that there are all the traffic to that destination, the certainty that you will not get a direct routing, and so you can allow yourself to remove those high energy prevention descent planning items in order to stay higher and, you know, allow fuel saving because you have used the engine at high altitude rather than at low altitude. Now, having done this programming of the FMS, what happens is that in this case the air traffic control is giving us a vector. You see, we are on heading 045, we started at descent, we found ourselves at level 250. So at this point my question becomes, okay, but what if the air traffic controls now give me direct to Oscar Sierra Tango or give me direct to Charlie Mike Papa to fly the approach? Am I high, am I low? What should be the distance from those points? Okay, well, both points we said would give us a 22 nautical miles to run from the threshold. So the 22 nautical miles itself is 6,000 feet. So now we are missing 19,000 feet. The 19,000 feet that we have to lose by doing altitude by 3, I could simplify, use 20,000 feet, by doing altitude by 3, 60 nautical miles, okay? In this, there is also the deceleration. Now, here the speed is not specified, so we don't know if we're actually descending 250 knots already or 300 knots. We should consider the deceleration, but I would say something like 60 nautical miles, so the 20,000 feet that I have to lose, 60 nautical miles is the correct answer. Now, because the exact number was 19, you see that here in the slide I got 57 DME, which is perfect. If you do a perfect calculation, as I say, I'm not looking at the mile here because we're very far away, fly level 250. So it's very difficult to analyze or to predict what will be the mileage. So I want to have a rough number that guarantee to me that I am on the correct profile. So if I'm 60 nautical miles from both points, I should be pretty much okay with the profile. Okay. In this example now, I find myself level 100. The air traffic controls has turned me on a heading of 090. Okay, and again, what should be my distance? As we said, 6,000 feet on both Charlie Mike Papa or Oscar Sierra Tango, remaining 4,000 feet. If I go by altitude by 3, the 4,000 feet give me 12, so I should be more or less 12 nautical miles. But at this point there is another doubt I should start asking myself is, okay, rather than being 12 nautical miles from those two VOR, what if the air traffic control gave me a direct to the final approach fix? Then I might find myself higher, because this time if I fly to Oscar Sierra Tango or if I fly to Charlie Mike Papa, I actually fly a longer route than flying direct to LOCRI. So I should start referencing from LOCRI rather than those 2 points. Those 2 points were good points for energy prevention calculation during the beginning of the descent. But now that I start finding myself lower and I realize that the ATC plan is not to make me fly through those 2 points, it's a bit useless to keep reasoning with reference to those 2 VOR. So I have to change my reference point of reasoning. And the easier way is to select another VOR, which is the Romeo Mike Charlie VOR, which is located right over the field. And by getting the DME of Romeo Mike Charlie, again, I start doing altitude by 3, which fly level 100 is 30 nautical miles. So I start reasoning with the VOR, which is over the field. Because I don't know what's the plan of the ATC. Maybe they want to vector me to very short final, like 4 nautical miles final. I don't know what's in their minds. So the safer thing is to change the reasoning and start reasoning with a VOR, which is over the field, and compare my altitude by 3 with the distance to this VOR. Okay. Now you see that we're flying around on the 090. I start having a clear idea. Now at this point I find myself at level 70. 7,000 feet. So it should be more or less 21 nautical miles plus deceleration. And at this point, I'm making reference to the DME, to the distance to the airport, which is a direct line distance. So I now start having a clear idea that, of course, not going to go 4 miles final. And the ATC probably is going to vector me with this heading. Maybe it's going to turn me a little bit more to the right, direct to LOCRI, having a shorter route, maybe a couple of miles shorter. But at this stage, you see that now that I have more or less 20 miles to run, at this stage, the games are done. I don't expect 30 nautical miles to run. It's impossible. I can't have 30 nautical miles to run. So now looking at the DME from Romeo Mike Charlie VOR, and from that DME, I determine what should be my altitude. So if I find myself like 20 DME, basically I should be 21 nautical miles plus deceleration, but the route I'm following is not a straight line to the airport, flying a longer route, so the deceleration should be there. And you see that this was a successfully planned descent profile. Of course, if the ATC will give me shorter route, I might need a bit earlier configuration, a bit of speed brakes or early gear. If ATC give me a longer route, maybe you're gonna need to add a little bit of thrust. But as I said, generally speaking, this profile was well calculated. So, as a conclusion on this altitude by 3 plus deceleration rule, we have to know what to expect. We saw that expectations are an extremely important ingredient. And of course, you have to use your experience, your situation awareness, other aircraft communication, knowledge of the airport, in order to be able to use this experience and to be able to plan your descent, okay? Without experience, you find yourself in an extremely difficult situation. Now, if you are in an extremely challenging, difficult situation, my recommendation is exactly what we did in the last part of this simulated descent profile approach. Place a DME over the field, keep yourself on a 3 degrees on an altitude by 3 ratio with the airport. So put a DME on the airport and keep yourself on an altitude by 3 calculation with the airport DME. If you always respect the altitude by 3 with the airport, there is no way you're gonna be high. The only solution is that you're gonna be low. So most likely you're gonna be low. But this will help you in preventing energy approach in a place where you are totally unfamiliar. But of course, familiarity will help you a lot. And know when to make correction, and this is something that we have to discuss, because we say how to realize, how to make the calculation, but when and how to make corrections, we didn't talk about it yet. We'll come to this in a moment. So as a final recap, we can give a little bit of example that's typical, I would say, generic European approach here. We're looking at Italy, Cagliari Airport, where you get in through a VOR, which is Charlie Romeo Alpha. You got the airway going to the VOR, then you got transition from the VOR to the ILS. And of course, you load this approach in the FMS. This will give you the profile. What could happen is that the ATC gives you a little bit shorter route. So you might consider cutting off a little bit the corner and intercepting the ILS at a lower distance. How short the ATC can give me the vectoring? Well, that's a very interesting question. It's something that the pilots should wonder about. How can I determine? Well, very often on major airport, you have a published minimum vectoring altitude. If the minimum vectoring altitude is high, the ATC cannot give you a big shortcut. Like, for example, in the case of Rome Ciampino I was talking about before, the minimum vector altitude is 3,000 feet because of the Vatican City. The ATC cannot vector you lower than that because the city of Rome. And for this reason, if the air traffic control can only vector you at 3,000 feet, the only place they can vector you is something like 10 nautical miles. But there are airports I've seen minimum vector altitude as low as 1,500 feet AGL. And if the air traffic control can vector you at 1,500 feet AGL, it means that he can vector you to something like 4 or 5 nautical miles final, which is very, very short. So to evaluate this shortcut, you might use, if available, the published minimum vectoring altitudes. Many airports has this downwind base and final vectoring as it is here. Very typical for Germany and Poland, where you have those arrivals. This is the Munich arrival, where you see that you come into one direction, then you got base coming to the other direction. This facilitates the vectoring for the air traffic control. Very rarely, actually, I wouldn't say never, because it happens when it's very busy. But I would say very rarely you fly this full procedure. The air traffic control, we use this procedure in order to sequence aircraft. So even if you have 2 or 3 flights, arriving at the same point at exactly the same time, by giving them shortcuts, basically they give them the arrival and then they give them a direct to the ILS, or a vectoring to the ILS. By vectoring them at different moments, they can sequence the aircraft. So the first guy, the lower guy, will get direct to the ILS earlier. The second guy will continue the arrival a bit longer, then get to the ILS. And the third guy, the higher guy, the third guy will stay on the arrival even longer time and then get to the ILS. So this is used for sequencing. So you should not expect to fly the full procedure, and in order to be safe, you should consider that from a reasonable point, initial point of the approach, you will most likely get a direct to something which looks like the 10 miles final. So you should consider this direct routing in your descent planning, as is, I would say, 99% chances a shortcut is definitely going to occur on this type of arrivals. Here we got an arrival in Paris, where you see that you got different arrivals. Very often what you get is that at some point you get to direct to a point, like it would be in this case direct to a point Omaco, which is not very shortening a lot the arrival. In French arrival, normally you get lower altitude. There's a number of at or below altitudes which will help you with the descent planning. So by loading this approach in the FMS will actually help you in a descent planning that will match more or less the altitude by 3 requirement. Okay, you might expect a direct to a point like, as I said, Omaco, which is something which brings you some 40-50 nautical miles to final, and after that, of course, you're gonna be vectors for the approach. So that's what it looks like. For example, if you have a bit of traffic, you see the ATC will guide you for a downwind base final in order to achieve a little bit of delay and separation. But in the descent planning, I would suggest you that you plan from Omaco direct to the 10 miles final in order to be able to accept a direct in the case there is no traffic. In UK, total different story. This is the arrival in Stansted. I've been flying there a lot, and this arrival brings you like 6 nautical miles from the airfield, and it would be totally useless in this case to make a proper descent planning in order to stay on a 3 degrees and be able to accept a 10 miles final. I can tell you by experience, over years and years of flying to London Stansted, I never had a direct to 10 miles final, even when runway 04, so the one which is the shorter in. I actually had it just once in my career, and we were very late at night, probably were like 3 a.m. in the morning. It was absolutely not a single traffic in the London TMA, and that was the only time in my life where I actually had a direct to 10 miles final in London Stansted. But this is out of probably thousands of flights I did to Stansted, and if you inquire with pilot that flies to Stansted, will be ready to bet that there's been pilots that have been flying much more than me, and none of them ever had a direct to 10 miles final. So in the specific case of Stansted, I would suggest you to respect, of course, the minimum of this profile, which will keep you high, and you will see that you have minimum holding altitude over Laurel of 7,000 feet. You're probably gonna cross Bravo Kilo Yankee Barkway VOR at flow level 80, extremely high, because if you do altitude with 3, is 24 nautical miles to run, and you're just 6 nautical miles from the airport. But from Barkway VOR, if there's no holding, then the air traffic control will guide you, will vector you to the final. So here is a good point to plan to stay high, because by experience, I can tell you, you're gonna be high. So that's how important experience is, because you have to be familiar with a specific airport. So that's what a route for Runway 04 would look like in London Stansted. As I said, don't even try to be on a 3 degrees glide with the 10 nautical miles final. You're not gonna get any shorter than this.
Paolo's Pilot Lounge. Like and subscribe now.
At this point, there's a last question that I have to answer to you, which I promised we will discuss, and is when and how to correct. Well, how to correct can be achieved in different ways. One of the ways to increase the speed above 250 knots, or anyway increase the speed above the economy speed. By increasing the speed, I increase the drag of the aircraft. Of course, you will tell me, yes, but I also increase the lift, because the lift is proportional to the square of the velocity, and also the drag is proportional to the square of the velocity. But if you remember, what happens is that when you increase the speed of the aircraft, you need less angle of attack because of the increased lift, and the highest wing performance, the highest wing efficiency, is achieved at higher angles of attack. So the lower is the angle of attack, the more you increase the ratio between drag and lift. So your wing is going to lose in efficiency. So yes, you increase the lift by increasing the speed, but you also increase the drag, and the drag is increasing at the square of the speed. So increasing the speed is a very efficient way to increase drag and lose wing efficiency, and therefore recover from a high profile situation. Another solution is to reduce the speed and configure the aircraft. Once again, if I reduce the speed and configure the aircraft, the wing gets less efficient, and with a less efficient wing, the aircraft will have tendency to descend a bit more. Other solution is to ask to the air traffic control to fly more track mile, and other solution is to use the speed brakes or aircraft spoilers. Now, when should I correct? Well, it's difficult to say when. For example, here I find myself level 410, and I pass the top of the descent. Top of the descent for level 410 should be something what 123 nautical miles from destination airport, and my FMS tells me that I am 1,000 feet high on the profile. Now the air traffic control is giving me the descent. Now, should I jump on the speed brakes and correct this profile? Well, there is a little rule of thumb, which I would say pretty easy, and the rule of thumb is 10%. So if I find myself 10% of the energy more than what I should have in the specific point, well, then it's moment to really move my back and do something. So if I find myself at top of the descent level 410, starting descending, and I see that I am 1,000 feet high, I probably won't take any corrective action, and I will allow the aircraft to descend on the calculated profile, see how is it going, because sometimes the winds are a bit different. So I might discover that I'm actually diverging from the calculated profile, and then yes, I have to do something. Or I might actually discover that the aircraft is slowly getting back onto the calculated profile, which means that there is no need to make any kind of correction, because the winds are slightly different than expected are helping me to get back on profile. Instead, if I would find myself like 4,000 feet high, well, I wouldn't just wait and see if I manage to get back. Okay, with 4,000 feet high at 41,000 feet, I think it's time to do something to correct profile. Now, being very high, the best solution in this case will be to increase the speed. As I said before, by increasing the speed, I reduce the duration of the flight. So I reduce the time I'm burning fuel inside the engine, so the aircraft gets more efficient. Increasing the speed is more efficient, of course, than using speed brakes, okay? Speed brakes is just wasting energy. Increasing the speed, there is a waste of energy because the wing is less efficient, but there is an increase of efficiency because I'm flying faster and the engines will be running at lower time. In fact, a high cost index, the aircraft will have an economy speed which will be fairly high for this reason. So increasing the speed will be probably the correct solution at 41,000 feet in order to correct profile. Now, before we continue to the next topic, let's put on the side some of the golden rule we have learned up to now. So the first golden rule is always consider the possibility of a direct routing, program your FMS accordingly, and keep yourself updated. If you realize that the air traffic control plan does not correspond to what you have initially programmed in your FMS, either keep your FMS updated, either disregard the FMS and keep reasoning with a different distance source, that could be the VOR, which is over the field. Of course, the altitude by 3 deceleration is the main golden rule. Never forget that. Always do this calculation as a backup of what your FMC is doing. Your altitude by 3 plus deceleration must always sensibly correspond to what your FMC is doing. And if you see that your total energy differ by more than 10% of the total energy that the aircraft should be for that specific point of the descent, start acting. Do a correction. Bring your aircraft back on the correct profile. Alright, at the point of this course, having understood the altitude by 3 COMSET and the threads of the shortcuts that might actually arise during the descent and approach, we have to talk about the aircraft total energy. This is an extremely important concept that all pilots must have, and certainly you have heard about it. I will be extremely surprised if you as a pilot get to the line and actually never heard about the aircraft total energy. So what we're going to do there is to use some schematics and try again to pinpoint some of the knowledge that pilots should have in order to have a more clear idea of what the aircraft energy is, in order to better manage the aircraft energy. So the pilot must be aware that the aircraft is provided with 2 energy, actually to be precise I should say 3, but in these slides we just have 2, which is kinetic energy and potential energy. Now, if that will be the case, you would be flying a glider, because there is another form of energy that you can add to the aircraft system, and this energy is the chemical energy contained into the fuel, that by burning fuel you transform this energy in engine thrust, meaning that you can add energy to the system. But mainly speaking, your aircraft is equipped with a kinetic energy and a potential energy. So what is kinetic energy? Kinetic energy is the energy which is contained into the movement of an object. Here you see a bowling ball is moving toward a wall, and eventually it would break down the wall. Well, here the question is, will actually the ball break down the wall? Well, the answer is I don't know. But if I tell you, say, okay, you don't know, but depending on what will the ball knock down this wall or not, you obviously tell me, well, it depends from the speed of the ball. If the ball is traveling fast, there's a lot of kinetic energy contained, and when it hit the wall, it will knock down the wall. If the ball is traveling slow, well, it will hit the wall, nothing will happen, okay? Well, that is the kinetic energy. So it depends on the velocity of the aircraft. The faster the aircraft travels, the more kinetic energy is contained into the flight, into the aircraft system itself. Potential energy is the altitude. So again, here you get the bowling ball which falls and splashes into a seau of water, and I'll ask you, okay, which one will splash more water outside? And it's quite obvious that the ball that is higher, that has more potential energy, has a higher altitude, will produce more energy by falling, by losing this altitude. And this excessive energy will result in a higher splash of water. Eventually, the one which is on a higher level will completely splash all the water outside the bucket, okay? So the total aircraft energy is kinetic and potential energy, the sum of those 2 energy. The energy cannot be disappear. Once the energy is created, has to be existing in the object itself. So the object aircraft once it builds up a number of energy, so converting fuel into speed, once this speed has been created, well, you cannot make it disappear. You can make the speed decrease by increasing the altitude, as you very well know, but you can't make the energy disappear in just 1 second. It will take time. Eventually the energy will disappear, but it will take time. Okay, so let's take this roller coaster example. Okay, what happens is that you have an electric motor that pull up the cart in the position number 1, and this cart now is at the highest peak. So what does it mean? Is that the electric motor provided energy to the system is the cart, and this system accumulated this energy in the potential energy. So there's no movement of the cart. Okay, at this moment this cart or this wagon start losing its potential energy as it starts descending. So as I go down the roller coaster, the wagon start accelerating and the kinetic energy start increasing. So I start transforming potential energy into kinetic energy. The initial energy actually came from electric motor. That energy became potential, and now with the descent I'm transforming potential energy into kinetic energy. When I get to the lowest peak, the point number 3, I got the highest velocity from the wagon, and this cart traveling very fast actually has the lowest potential energy. So the total energy in the system is actually the same. The energy that the system cart or wagon had in point number 1 is identical to the energy that the system has at point number 3. There is only one little difference, that some of this energy were wasted, were dissipated, because during the movement, because of the movement of the cart, there are resistances. There is friction between the cart and the rail, the wheels of the cart and the rail. And those friction will absorb energy, which is actually transformed into heat, noise, and other vibrations. But anyway, all these things, they actually require energy. And this energy is coming from the system cart. So it's coming either from potential, either from kinetic. I would say mainly from kinetic, because the resistance is the result of kinetic movement. But as a matter of fact, as the cart moves, there is a waste of energy on the way down, which means that it's not exactly true that point 3 is equal point 1, because point 3 you had all the losses of the resistance that the cart encountered during the descent in this roller coaster. Okay, at this point we get the second hill, and as you very well know, on the roller coasters the second hill is high, but is always a little bit lower than the first one. Why this? Because of the resistance losses. So we don't want the cart to stop and go back, we want to keep it going forward. So on the hill, uphill, you're gonna start losing speed, you're gonna start again storing the kinetic energy into potential energy, but the roller coaster will never reach the same level because the engineers accounted from some kind of losses, and so the wagon must maintain a minimum of kinetic energy in order to reach the peak and start descending again for the second descent. So this roller coaster is a typical example on how to convert energy. On the aircraft we say it fuel energy, chemical energy coming from the engine. We can convert it into altitude, we can convert it into speed. At the end is what we do during takeoff. What do? You apply thrust, and this thrust is used to increase aircraft kinetic energy. You are not climbing, you are resting with your wheels on the runway and just increasing kinetic energy. But when the speed is enough, when the kinetic energy is enough, you actually keep your speed constant. So you fix your kinetic energy at the V2 or V2 plus 20, whatever speed it is, and now you start converting the chemical energy into potential energy because you want your aircraft to gain altitude. That's what we do on the takeoff rule at the end of the day. So if you want to make a nicer scheme of this aircraft system kinetic energy. We have here on the slide two bottles of waters, two buckets of waters, because energy can be compared to water. And one of this bucket is called altitude, guess what? The other bucket is called ES, indicated airspeed. So potential energy, kinetic energy. And what happens is that the pilot, as we know, has a throttle. The throttle converts an amount of chemical energy, fuel, into, we say, either kinetic, either potential. And that's what the pilot can do. You see, with the throttle, with the use of the throttle, you can give maximum thrust to your engines. It will take time, even if you stay at maximum thrust, to dry out the fuel tanks. It might take hours. So it's gonna take a long time to convert the fuel energy into kinetic and potential energy. And that is the problem. You have very limited capacity to produce the energy. So to increase the altitude, to increase the speed, airliners, they're very heavy, so compared to the weight of the aircraft, the engine, though being very powerful, cannot add so much energy, cannot add so much potential energy, so much kinetic energy as you would want. You're not a Eurofighter where you can climb vertically, for example, okay? So with the throttle, you decide to give thrust, and in this scheme you see that actually here you got water flowing in both altitude and ES. So, well, this will be a kind of initial climb where you slowly increase the altitude, but you also slowly want to increase the ES, so you are dividing both of them. Actually, how do you decide whether you want to store this energy produced by the engine in the altitude or in the speed? Well, the answer is the pitch. So whether you want to add energy to the system is the throttle, but where you want to store this energy in the system is the pitch. So you see that there is a second valve here, which is pitch, and in this case is what you have during takeoff roll, okay? You see that you got full throttle, you got full thrust, and despite having full thrust, because the pitch is for level flight, the altitude remains constant, and what is increasing in this case is the indicated airspeed. So this is the scheme of what would happen during takeoff. Now, once the indicated airspeed is enough for the flight, then I use the pitch, I increase the pitch so that I start storing the engine energy into altitude rather than into an increased speed. Now, as we said before, the more you increase the speed, the more resistance you produce. The higher the speed, the lower the angle of attack. The lower the angle of attack, the less efficient is your wing. So in terms of waste of energy, you see that in the airspeed bucket there are a little bit of white lines, you know, of leaking points, I would call it. So the bucket of airspeed is leaking very easily. The more you fill it up, the more resistance the aircraft has, the more there is a leak in the system. And also the pitch, you see that there is a leak in the pitch. Yes, because even if you try to be as much efficient as possible, the aircraft will always have aerodynamic resistance. And this aerodynamic resistance will always correspond to a constant loss of energy. So even if you take a very low airspeed, minimizing the losses of energy, well, there's still gonna be a loss of energy to keep your aircraft flying. And that's actually what you do when you fly a glider. You know, you just preserve your energy, try to optimize the energy you have in order to maintain the longest flight as possible. And then of course you use thermal currents, you use environmental factor to actually gain altitude. In the second slide, basically we've been climbing for quite a long time, so we have stored a lot of energy into the altitude. The aircraft gained a lot of altitude, and finally the pilot decided now to switch the pitch to the airspeed indicator. Throttle has been slightly closed, it's not fully open, so yes, there's still energy provided, but not the maximum amount of energy. And the airspeed has increased a little bit, so now you see that we have, I think, two little white lines that became blue, and they're producing this aerodynamic drag, so this leak of energy during flight. At this point, what happens is that the pilot intends to start his descent for the landing. So of course we need to empty both boxes. We need both buckets of water to become zero. So the altitude has to become completely empty, the airspeed has to become completely empty. And how am I going to do that? First of all, stop providing energy to the system. So the throttle goes to completely zero. Actually, it's never going to be zero, as you very well know. The engine thrust as a minimum. So I'm just going to reduce the engine thrust to a minimum amount of thrust. And this minimum amount of thrust, of course, is not going to be enough to maintain the level flight, which means that I need to descend in order to keep a minimum airspeed of the aircraft. And that's what I want to do, to descend. So at this point, I use the pitch in order to maintain constant airspeed. And what I'm doing, I'm transferring water from the altitude bucket to the airspeed bucket, because the airspeed bucket is the one that continuously gets emptying because of the aerodynamic drags. So because it continuously gets empty, I need to continuously transfer water into that tank in order to maintain an acceptable level of energy, of airspeed for the sustained flight. At this point, let's presume that we find ourselves high on profile. As I said before, when should I correct? More or less 10%. So let's presume that we are in that example, or we are now, say, 30,000 feet, okay, for level 300. I do my calculation, should be 90 nautical miles, and actually I find myself something like 80 nautical miles. Hey, that's 10%. So, well, that's the moment to do something. What could I do? As I said, one very effective way to improve the rate of descent and maintain aircraft efficiency is to increase the airspeed. Because by increasing the airspeed, I reduce the time we're in flight, I reduce the time I use the engine, I reduce the wing efficiency, so I have a steeper angle of descent. So that's a good idea. So what I do is that, as you see in this slide, I use the pitch to transfer even more altitude liquid into the airspeed liquid. Now the airspeed is basically at the maximum speed the aircraft can fly, and because I'm the maximum speed the aircraft can fly, as you very well know, as we said before, I have to reduce the angle of attack. By reducing the angle of attack, the resistance remains very high, but the lift is relatively low because of the low angle of attack. The wing is working on a relatively low efficiency. And that's it. We can see that from the yes, we are leaking a lot of energy. So the amount of energy we're losing in the same amount of time is now higher than what we were losing before. If we have to make a skim on the aircraft descent, basically we were planning at 260 knots in this example, 260 knots descent. And what happens, because I decided, or I found myself higher, so I decided to descend faster, well, I'm now descending on a steeper descent at 330 knots. Now there's one thing which is interesting to note, and is this area of overlap of the two curves. Obviously, if I reach level 100, where I have by law to decelerate 250 knots, if I reach the proximity of level 100, 260 knots, the deceleration is going to be very short, just 10 knots deceleration. But if I reach that level at 330 knots, I'm going to have to make a 80 knots deceleration. So the deceleration ramp is going to be significantly longer, very significant, I would say. And this means that I have to reach the deceleration ramp at an earlier stage. So at some point, my high energy profile, my high speed descent profile is actually descending below the 260 knots standard speed profile, because I need to build up more room to provide the deceleration. After that, of course, I will continue descending 250 knots.
Paolo's Pilot Lounge. Like and subscribe now.
Now, let's presume that the increase of the speed has been sufficient to recover the profile pretty fast. And when I talk about recovering profile, we have to talk about kinetic energy and potential energy. So not only being on the diamond, not only being on the altitude. Whenever we talk of profile, we have to think about that little diamond that the FMS give you, vertical profile, and the airspeed is the marriage of the two. Remember that your profile is an energy profile. So your profile is not only the diamond, is altitude and airspeed. But let's presume that I am back onto this profile, okay? And at this point, I go back to 260 knots. Well, this slides shows again the picture. I started transferring back water from the airspeed to the altitude, meaning that I reduced the loss of altitude, and I now started descending 260 knots, and that's what we have on this slide. At this point, let's presume that the air traffic controls tells us, okay, maintain level 280, whatever level it is, because there is traffic, I can't give you descent. It happens sometimes that you can't get descent and you start feeling high on your profile. Well, what happens, as I say, because a profile is energy, the fact that the ATC lock you on a profile and does not give you descent does not automatically means that you lost your descent profile. Yes, you will see that little diamond going away and the pilot has this stressing feeling that is getting high, but as we said, the descent profile is an energy profile, meaning that if you are on that correct energy profile, if your energy is correct, and if you are not adding energy to the aircraft system, you are still on that profile. You are not losing the profile. You can see the diamond going down, but the energy of your aircraft is correct if you don't give thrust. And this is what is happening on this slide. The pilot keeps the thrust at idle. So the game in this case is to keep the same amount of energy in the system. So do not give thrust. You level off the aircraft, you have to maintain constant altitude, and what you start doing, you start losing speed in order to maintain the altitude. As the time goes by, the bucket of the ES is getting empty. So before it was 260, now maybe it's 240. Time is going by, it's going down to 210. Now, at this point, as I said, if you manage smartly your automation, or anyway, if you're flying manually, which in this case I wouldn't suggest for the management of a descent, of course the automation is highly preferred, but what would happen is that you have to add thrust to maintain the level flight, because the level 280, you're too high for extending flap. You cannot go below the maneuvering speed, so you're stuck. You have to fly 210 knots minimum. Now let's presume that luckily at this point the air traffic controls pop up and say, okay, you and I continue descent level 100. So finally we can start our descent, or we can rejoin our descent. Now what happened is that we completely emptied the bucket of the airspeed, but we kept the bucket of the altitude at the same level. What the FMC calculated, or what we expected, is to have constant airspeed and constantly decreasing altitude. But as I say, the total energy in the system remains the same. So I didn't waste anything. So all I have to do here is now to pitch down and transform what I didn't lose altitude. Well, I transformed this altitude into kinetic energy. So basically I bring back the aircraft at 260 knots, not by giving thrust, because I don't want to add energy to the system, but simply by pitching down, best mode level change, 260 knots, pitching down, the aircraft will make a real big dive, converting a lot of altitude into kinetic energy, and I will have a massive loss of altitude. And I will find again on my descent profile for 260 knots, because in this system I didn't remove any energy and I didn't add any energy. Actually, the only energy I didn't remove is that by decelerating, the wing became a little bit more efficient. So maybe if before I was on profile, now it could be 100, 200 feet high, but no more than that. So the maintaining of the altitude and losing of the airspeed was a technique to maintain the profile, to maintain the energy profile. And if 260 knots was my economy speed, by doing this maneuver, I actually maintained the economy profile without the need of doing further calculation, further recalculation of profile, or having the need of correcting the profile. So if you want to see in graphic what we have been doing, we were descending 260 knots. We level off at level 280 because the air traffic control didn't give us a descent. You see, we maintained the altitude, arriving 210 knots. Luckily enough, the ATC luckily told us, clear of traffic, you can now resume your descent to flight level 100. And that's what we did. We dived down, increasing significantly the speed, losing a lot of altitude to recover the speed, and we got back on the VNAV profile, on the ideal profile. Good, let's take another example here where, same as previous descent, we calculated an economy descent at 260 knots. The pilot is descending in economy speed 260 and is perfectly on profile. And this time, same thing, the ATC stopped me at level 280, so same as we explained before. What I do is leveling off and transforming the kinetic energy into the maintaining of altitude in order not to add energy to the system. But what happened is that, unfortunately, the air traffic control this time does not give me further descent. So I reached 210 knots, the auto thrust started giving thrust because otherwise I would stall the aircraft, and still waiting for the crossing traffic to be on my TCAS or to have visual contact with this conflicting traffic. So what I have to do, well, I have to give thrust. Now I am adding energy to the system. So now I already know that I'm not anymore on the 260 knots energy profile. That profile is gone forever. And I have to calculate the new energy profile, more resistance, more draggy, with less efficient wing, in order to recover the descent profile. So on the next slide, that's what I will do as soon as I get descent. Now, because I was giving thrust and I was modifying my profile, it is quite useless to try and recalculate a profile for as long as I don't know what my profile is. For as long as the air traffic control does not give me a descent, I can't recalculate my profile. I just know that I'm high, but how much high? How to recalculate? Well, that's a bit difficult. But as soon as I get the descent, of course, what I will do is to stop giving energy to the system. So throttle back, thrust idle, level change function for this will function very well. And same as I did before, in the case where I actually had the descent, well, same as I did before, I'm gonna do the same thing. I'm gonna increase the speed at the maximum and have the aircraft diving down. So transforming as much possible altitude into airspeed. Why I want to transform altitude into airspeed? Because the highest the airspeed, the highest the drag, and the less efficient is the wing. So basically, I'm converting my aircraft into a less efficient descent, which still is better than using speed brake, as we said before, because a fast descent means that you keep your engine running for less time. So it remains still the most efficient descent for the newly given situation. If we have to see in graph what we have been doing as compared to what we had before, you see, before we level off, we reached 210 knots, then we started diving down, we were on the same profile. Now what happened is that in orange you have this segment where we've been adding thrust. All this segment is a segment where there is an additional energy added to the system. So now the system needs to waste this energy. And how can I waste this energy? We say by diving down. You see, when I was diving down 260 knots, still now I was above the profile because I added energy. So I cannot say, okay, just gonna descend 260 knots. So what I can do is to accelerate to the maximum speed I can get, like 330 knots, I would say, or 320. What makes you comfortable when it comes about high speed, okay? But the highest speed I can produce with my aircraft, in order to have the less efficient wing as possible, and in this way to have a steeper angle of descent. Not the standard 2.8 degrees, but something that might look more like a 3.2, 3.3 degrees descending at 330 knots. So basically I reach 330 knots. As I reach 330 knots, I keep descending 330 knots, but then I have to manage my deceleration from 330 knots. So again, in this graphic, you see that the ramp of the 330 knots actually end up into the deceleration ramp. But there is a problem in these slides, is that that blue deceleration ramp was designed to decelerate the aircraft from 260 to 250. Now I have to decelerate the aircraft from 330 to 250. That's 80 knots to be lost. And if we use our previous calculation, between 330 and 260 we have 70 knots, so I would need 7 more nautical miles if I actually rejoin the diamond, the vertical profile of the FMS. If I rejoin that vertical profile at the beginning of the deceleration, I actually will need an extra 7 nautical miles to lose the excess energy that I have in the kinetic energy. So I still have to manage my energy after deceleration. So my deceleration is going to be longer than expected, and I'm still going to find myself high on profile. Now, we in this scheme can add other ways to lose energy from the aircraft. Below level 100, we can refine our scheme here by adding these controlled leaks. Those controlled leaks that you see there, they're designed on the high speed area because the resistance is square the velocity. So the more I fly faster, the more effective the resistance is, obviously within the limitation of the flight control that I'm using. So obviously if I extend flaps, I have to respect the maximum speed of the flaps. But you see that in this scheme we added FF, so flap 1, flap 5, which of course includes the slats, and the S for the speed brakes. So there is each pipe leaking for flap 1, each pipe leaking for flap 5 for the speed brake, and then we got 3 pipes for the gear. As 3 pipes, easy to remember. The gears are 3 landing gears, so obviously you got 3 times the leak, okay? And that's the way you remember that the gear obviously is much more drag than the flap or the speed brake. In numbers, another rule of thumb is that we can have this idea of the bucket of energy, okay? So we can do our calculation in terms of buckets of energy, and one energy unit is 10 knots. 10 knots equate to 300 feet, or with the altitude by 3, as we said before, 1 nautical mile. So if I have 300 feet, I can glide for 1 nautical mile. If I have 10 knots, I can fly straight level for 1 nautical miles, and I will lose this energy. Aircraft energy in numbers, in practical numbers. When I fly at 220 knots, the vertical speed will increase by the numbers that you see on these slides. Meaning that the 737, when you are at approximately 220 knots clean configuration, will descend with a vertical speed which varies between 1,000 and 1,200 feet per minute. You can increase this vertical speed by the values that you see on this slide. So by selecting flap 1, 300 feet more, you can descend at least 1,300, 1,400 feet per minute. You go flap 5, you get another 300 feet more, meaning that you can descend 1,600, 1,700 feet per minute. Use flaps 5 and speed brakes. Well, you can now descend something that is approaching 2,000 feet per minute at 220 knots. That's very important. Don't reduce the speed. I see very often pilots that they're high on profile and they start reducing the speed. That's totally wrong. If you reduce the speed, you lose the advantage of the drag. So you can only allow yourself to reduce the speed only when you're certain that you have the profile. Once you're certain that you are on the correct profile, that you can get correctly on the approach profile on the glide slope and not above it, only then you can start reducing the speed. Don't reduce the speed before, because if you reduce the speed before, as I said, you reduce the drag, okay? Here we are talking of what to do once you are in a range of 20 nautical miles. That is the key point. You remember before we said in orange. So I reached 10,000 feet, and it's the moment where I say I should be more or less 30 nautical miles. But after that, as the ATC is guiding me, I start having a clear idea of what is the remaining mileage, and my reasoning switch the other way around. I say, if I am 20 nautical miles, what should be my distance for 20 nautical miles, okay? And 20 nautical miles, again, altitude by 3 is something like 6,000 feet, depending on the speed, because I have to take account of the deceleration. So 6,000 feet with 220 knots, it's a okay position. So, as I said, you do your reasoning based, this time reasoning distance, what should be my altitude. If I don't have that altitude, I can increase this rate of descent. So for example, slightly high at 20 nautical miles, I can easily decide to use the speed brake and increase the rate of descent by 300 feet per minute. If I am significantly high, as it was in the previous example when I showed up at 330 knots instead of 260 at the beginning of the deceleration amp, with 80 knots more, 80 knots more is, or 70 knots more, sorry, well, 70 knots more is 7 nautical miles, okay? And 7 nautical miles is something around 2,000 feet, so I'm 2,000 feet high, okay? If I am 2,000 feet high, probably the speed brake is something completely useless at this stage and need much more drag, okay? Now, if you use the landing gear, as we say, times 3, so the landing gear alone will give you something like 1,000 feet per minute rate of descent increased. Meaning that if you are 220 knots, clean configuration, descending more or less 1,100 feet per minute. If you go gear down, you're now descending something around 2,200 feet per minute. If you go gear down flap 5 at 220 knots, you are developing 2,600 feet per minute, which is a massive vertical speed, and you will definitely recover your profile if you're high. So knowing these numbers is very useful because it helps you understanding when you have to be aggressive or how much you should be aggressive in correcting the profile if you find yourself high on profile. Well, in this picture here, you see that we are above the glide slope, 210 knots, and we're clean configuration. So this is the case where I say, well, if you find yourself in this situation, you're in a bad situation, because that's exactly the moment where the captain is going to be like, hey, do something, because we're too high. Still, we're far out, we're 6,000 feet. So here the DME is not showing, but because we're probably too far away. The 6,000 feet, we should be something like 20 miles. So basically we're on a very long final, 20 miles out, and we find ourselves high on profile. We're below level 100. How am I gonna manage this? Well, as we said, extending configuration, extending flap will help me in fixing the problem. You see that what we're doing there, we extended to flap 1, and you see, as we extended flap 1, we also selected 220 knots. The aircraft is now increasing significantly the rate of descent because it has to recover this gap of 15 knots. At this stage, we're here with flap 5. The aircraft still didn't recover, and we have 2,200 feet per minute. So once this 10 knots recover, of course, the rate of descent is going to be decreasing. But you see that simply by configuring and increasing the speed at 220 knots, I'm actually bringing the aircraft back onto the correct profile. And because with flap 5, I know that this aircraft will descend slightly more idle thrust, slightly more than 3 degrees per second. We say there's something around 1,800 feet per minute on a ground speed that here should be around 250 knots. So if you have a ground speed of 250, the 3 degrees, as you know, ground speed multiplied by 5 is the rule of thumb to get the 3 degrees vertical speed. So if I do that rule, 250 knots ground speed multiplied by 5 would give me 1,500. And I just say with flap 5, we get a minimum of 1,600, 1,700. So we're descending slightly more than 3 degrees. Because we're very far out, we reasonably gonna be able to recover this profile. Without going any forward in our video, I would like to spend a word about our today's sponsor, which is the Aviomar Flight Academy. In particular, I would like to talk about the advanced courses, because Aviomar is well known for the basic courses like PPL, CPL, ETPL, which might be provided as modular or integrated. In particular, I would say the Ryanair Future Flyer Academy is a great product that gives pilots a direct entry to the Ryanair company, but I would like to talk about the type ratings, instructor courses and examiner courses. In fact, I did personally the mistake of having a type rating expired. Well, what happened is that I found a job on a different company and I was type rated on a new aircraft, on the 737, so I left my previous type rating expiring. And that was a mistake, because I thought I would never need it, but I was wrong, because what happened that when I became instructor and examiner, I then realized that I could move my instructor and examiner rating to the previous type ratings if still active. So, because I let my type rating expiring, well, what happened is that I couldn't transfer my type rating. So basically, I lost the privilege of instructing and teaching on that specific aircraft because I simply wasn't rated anymore. So my recommendation, and this could be the case especially to pilots that, for example, have an Airbus 320 and find a job on the 737, my recommendation is that, of course, you keep your type rating alive, because your type rating is worth a lot of money. It just take a check session. So check here in the detail, come to the flight school and ask for detail for the revalidation and renewal courses that are available. As I just said before, Aviomar also provide courses as type rating and synthetic flight instructor, and also synthetic and type rating examiner. So if you're interested to give a boost to your career and to get value on your license, well, again, come to the flight school for further details.
Paolo's Pilot Lounge. Like and subscribe now.
Alright, this brings us to the conclusion of the understanding of the topic of the aircraft energy. Let's put on the side some of the rule of thumb that we have learned at this stage, which is, first one is that the bucket of energy, we can call it bucket of energy, the 10 knots corresponds to 3 nautical miles, corresponds to 300 feet. So with the altitude by 3, basically, if I have 1,000 feet to lose that energy, I need 3 nautical miles. If I have 30 knots to lose the energy, I need 3 nautical miles. I will be on the same energy profile if I don't add energy to the system. Once I have added energy to the system, I am on a higher energy profile, therefore I need to descend faster in order to meet a new energy profile. And then we discuss this rule of thumb, which is very useful on the 737, which is the rule of thumb of the flight level change 220 knots. 220 knots is called the magic speed on the 737 because it actually allows you to do a lot of things. For example, gear extension and retraction, flap extension to flap 5. Let's say it's a speed that is very convenient whenever you have any technical problem or every situation that makes you overload. Flying 220 knots is a safe and convenient speed, and that's why it's called the magic speed for the 737. And on the 737, at the magic speed at 220 knots, we say you are descending 1,000 to 1,200 feet per minute in level change, which is giving you an angle of more or less 2.8 degrees. But you can increase this angle by 300 feet for each flap selection, 300 feet for the speed brakes, and 3 times 300 feet, 900 feet if you select gear down. Those are safe numbers. The actual aircraft is going to descend more than that, so you will see that this actually will bring you a bit lower on energy, so you will find yourself a little bit facilitated in recovering the profile as compared to those safe numbers. Let's move forward to the third aim of this course. We have to talk about the logic of the VNAV. As I said, modern aircraft use VNAV, so as a modern pilot, you have to know how to manage the VNAV. And I would say the golden rule, always insert correct data in the FMS, because garbage in, garbage out. So make sure that what you're inserting It's not garbage. If you don't have data, don't insert it. Let the FMS open. Sometimes it happens, I see crew that they fly having weather data which is based on weather which was maybe 18 hours before, 12 hours before. Well, at this point, the weather information is not that accurate. Don't load it in the FMS. I know that many companies has it as an SOP, but don't be stupid. It is an SOP, it is a good practice if the data is accurate. If you have inaccurate data, don't load inaccurate data into your FMS. Otherwise, your descent planning is going to be incorrectly calculated. Now, the FMC logic is exactly to produce the ideal profile that we discussed at the beginning of this course in the objective. So, an FMC vertical profile as calculated as much close as possible to the ideal profile that we presented in the objective of this course at the very beginning of the course. So the ideal descent profile where from top of flight I reach basically short final and then I give thrust in very short final. Well, not always is possible because we or the airspace organization insert an amount of constraints. Now, if we go back to the approach in Ciampino that I discussed in the previous example, you see that what happens, for example, here I gave the FMC with an economy speed of 270 knots, so the cost index is such that we get 270 knots. We are descending at 270 knots, but then we reach level 100, so we reduce 250 knots. And you remember what we did before is to force the altitude at Oscar Sierra Tango VOR 6,000 feet because that was a high energy approach prevention point. So that was a way to prevent that a shortcut would cause us to be too high. And because I inserted 6,000 feet there, then the FMC is creating a straight level flight segment between Oscar Sierra Tango and Charlie Mike Papa, which are both points forced at 6,000 feet. Now, because I inserted 6,000 feet or below a Charlie Mike Papa, you see that eventually the FMC calculate at beginning of descent, which is slightly before Charlie Mike Papa. But as a matter of fact, there is this straight and level flight because being 6,000 feet at Oscar Sierra Tango and flying the all arrival, it's definitely taking us too low on profile. So the FMC will calculate this profile. I gave you this number with the 500 feet deceleration, more or less of level 100, 200 feet per minute, more or less deceleration from the beginning of the deceleration from 250 point to what I am still calling the mystery point. And the mystery point is where this deceleration ramp connects with the 3 degrees that brings you on the runway. At this point, logic of the VNAV. The cruise descent of the VNAV on the 737 is a very stupid logic, so don't overtrust it. That's one of the cases where you should not use the FMS for descent planning. In fact, if you are in cruise descent, you are not in descent mode. You are technically in cruise mode. During a cruise descent, the FMC doesn't do any calculation about the descent profile. So do not look at the descent profile in that case, because the FMC is not calculating the descent profile. Once you finish the cruise descent and you are at the new cruising level, the FMC will recalculate the top of descent for the current cruising level, meaning that eventually it will discover that the descent point was behind us. So that's why it's a good practice to always have awareness of a rough calculation of what should be our descent point, because you could cross the descent point during a cruise descent. So the cruise descent is what you do when the ATC give you early descent. Sometimes they give you descent level 320 and you have to fly for a long time at level 320. So you just go in, punch in the FMS level 320, you get a 1,000 feet descent, constant vertical speed descent from the FMS. That's cruise descent. And you can see from the title of the page of your FMC saying cruise descent. This is in scheme what I was just saying. Could be that you are doing a cruise descent to the flight level 250, but during the cruise descent, the FMC is not, depending on the update actually. In some cases you could see it, but generally speaking, don't take it as granted that the FMC will give you a top of descent from level 250. I tell you honestly, once you inserted a cruise descent normally the newest update of the FMC will actually give you a top of descent. So you will actually see the top of descent along the magenta route on your navigation display. But again, use caution, because that is top of descent from level 250. And as is shown in this graphic, you are still descending in cruise descent phase. So maybe you will cross the top of descent of level 280. So you find yourself 3,000 feet high. So that top of descent is assuming that your aircraft is at level 250. During cruise descent, the FMC cannot calculate a complete descent profile for you. For the VNAV descent, we have two possible logic for the descent, and it's extremely important that you look at the fly mode annunciator and you carefully read on the pitch column whether you are descending in VNAV path or VNAV speed. This is extremely important because the FMS does automatic changes from VNAV path to VNAV speed and vice versa. Therefore, you might think that you are in a mode and you're actually using a different mode. Now, the VNAV speed, as the word says, means that the aircraft pitch has been coupled to the speed. So the FMC is commanding a speed and the pitch is going up and down to chase the speed. That's exactly the same logic of fly level change. The VNAV speed, okay? In the VNAV path, the FMC has coupled the pitch to the calculated vertical profile, so the aircraft stays on that profile, and that profile of descent should correspond to the speed. So at the end of the day, in a perfect world, the two things are exactly the same, because if the vertical profile has been correctly calculated, when I go VNAV speed, the autopilot is chasing the speed, but it turns out that being on that speed corresponds being on the VNAV profile. If I am VNAV path, the FMS use the pitch to stay on the path, but it turns out that staying on the path with thrust idle correspond to that specific speed. But this is in an ideal world, so normally that's what happens and it works well. But sometimes it doesn't. Sometimes it happens that you are in VNAV speed, you realize you can't make up the profile, or you are in VNAV path and you realize you are losing control of the speed. So you have to do something to fix the problem. Once the FMC senses that you are in the approach, therefore the flaps are extended, or you're missed that point that I called the mystery point before, so the point where the aircraft starts the descent with the final descent angle, then the approach logic will engage, meaning that the only mode acceptable on the FMC is the VNAV path. There's more or less the same logic of the ILS. On the VNAV path, the aircraft sticks to the vertical profile. On the glide slope, the autopilot will follow the vertical profile, and basically you or the auto throttle has to manage manually the speed. But that's what we said. That's what you should do when you start to be within the 20 nautical miles. When you are within 20 nautical miles, you have to be very aggressive, same as the VNAV path, very aggressive in recovering the correct vertical profile. Once you are on the correct vertical profile, then you use drag accordingly your need, or thrust accordingly your need, in order to have the correct high speed. But don't get high on profile, because otherwise you won't be able to fulfill the requirements of the approach. Now, among the required knowledge of the VNAV, there is the fact of knowing what is the VNAV logic when you engage VNAV by being below the profile. Once you are below the profile and you engage VNAV, the FMC will systematically engage in VNAV path. Well, I should be a bit more politically correct and say typically engage in VNAV path. Because, as I said before, the FMS has so many logics. I can't be so sure that it's always systematically VNAV path, but yes, typically it's going to be VNAV path. And what is the logic of VNAV path from below profile? The logic of VNAV path from below profile is to give thrust in order to maintain the economic speed and to rejoin the ideal descent profile with a vertical speed of 1000 feet per minute. So the VNAV path, for example, in a descent is very useful when you get early descent and you're not doing a cruise descent, but you actually activated the descent phase in the FMS. So if you are active descent and the ATC gave you an early descent, using VNAV path is very comfortable, I would say, and safe. Why? Because it gives you a minimum rate of descent of 1,000 feet per minute, which is a good rate of descent. And at the same time, if you get distracted, you don't get high on profile, because you have 1,000 feet per minute, but once your aircraft, after a long time, maybe after 20 minutes of descent, reach the VNAV profile, well, the VNAV, we now go thrust idle and start descending on the VNAV profile. So using VNAV path for the descent is a very comfortable and useful tool if you know how to use, and you know that it uses 1,000 feet per minute. But it's not always the case. For example, a typical mistake that occurs is that you are below the profile, you are using VNAV because you know that we, the captains and instructors, like when you use VNAV, so you make us happy by using VNAV, but at this point the ATC pop up and say, reduce speed 2 to 0 knots. If the ATC asks you to reduce speed 2 to 0 knots, I just told you before that the 737 idle descent at approximately 1,000 feet per minute, 1,000 to 1,200 feet per minute. That's the number that I just gave you a few seconds ago. So if you insert 220 knots in the FMS, you find yourself below the profile and you engage VNAV, the VNAV descends with the below profile logic. So commanded speed on the autothrottle 220 knots and vertical speed 1000. But because vertical speed 1000 is actually the loss of vertical speed that you have to maintain 220 knots, if you find yourself at 250 knots, descending 1000 feet per minute, you will never lose this excess high speed. So the air traffic controller assigned to you 220 knots, you did everything it was theoretically needed on the computer. So as a computer programmer, you did your program correctly because you inserted 220 knots in the FMS, you inserted VNAV, you let the FMS fly the aircraft. So congratulations, yeah, you're a very good programmer. But as a matter of fact, the logic of the FMS with the descent of 1,000 feet per minute would not allow you to lose the speed, and the air traffic control wanted you to maintain that speed. So a typical mistake would be, for example, descending in VNAV, being below the profile during deceleration during an high speed assigned by the ATC. The most convenient way to descend when the ATC gives you speed is level change, because you couple the pitch to the speed. So you go level change, you're certain that you're complying with the air traffic control airspeed. Now again, if the air traffic control assigned to you 280 knots speed and you are below the profile, you can confidently go in VNAV, because you know very well that with 1,000 feet per minute to maintain 280 knots, the aircraft is going to need some thrust. So basically VNAV in that case is very efficient. So again, be smart, know your aircraft, know the performance of your aircraft, know the logic of your aircraft in order to make the appropriate selections. Okay, in this example, ATC tells you 280 knots below the profile, you can use VNAV path. The ATC tells you 220 knots you're below the profile, don't use the VNAV path. Go level change, make sure that that speed is granted, because VNAV with 1,000 feet per minute is not going to be able to maintain the rate of the descent.
Paolo's Pilot Lounge. Like and subscribe now.
In these slides, we have a recap of what we just said, what could be the logic of the aircraft in the various phases of flight. So you see that for this aircraft, which is above the profile, if you use VNAV path, the aircraft will dive down and regain the profile. The usage of VNAV path could cause the aircraft to lose control of the speed and eventually go in overspeed. Now in this case, the VNAV should engage in VNAV speed, meaning that the aircraft will maintain the calculated economy speed or the calculated speed that the pilot loaded in the FMS, but this speed could result in having the aircraft remaining above the profile. However, once the FMC transition into the approach logic, as we say, the FMC will not accept any deviation from the vertical profile. The FMC will transition automatically into VNAV path. So when the FMC transition into approach logic, you see at this dot, the FMC goes in VNAV path and dive down like crazy in order to regain the vertical profile. In the second example, we got the case where we're below the profile and the VNAV path works very well. Say that your economy speed is 260 knots, you are below the profile, you go VNAV, VNAV 1000 feet per minute logic will allow you to regain the ideal profile with a rate of 1000 feet per minute, and you know very well that with 1000 feet per minute, 260 knots, the aircraft is going to need a little bit of thrust. So basically, you're not going to lose control of the speed because the rate of 1000 is reasonably low. In the third example, the aircraft is significantly low below the profile. No matter the speed, if I keep descending 1000 feet per minute, I will basically, I'm bringing my aircraft too low because I'm very, very low on profile. And 1000 feet per minute is not a consistent vertical speed to regain my vertical profile. So the best way in this case, if I'm extremely low, probably would be to use vertical speed like 200 feet per minute, 300 feet per minute, trying to regain a decent vertical profile in order to avoid a complete level off of the aircraft. There are tools that we will see in a moment in order to achieve this. So this brings us to the conclusion of our understanding of the VNAV logic. Obviously, here I've been extremely short. We should talk about hours on the VNAV, how to program the VNAV, how to interpret the VNAV. This was just an introductory information and just a small discussion, but we can pull out some golden rules here as well. And the golden rules, of course, is the energy cannot disappear. You can just transfer for kinetic to potential. Second rule, we said the energy of 300 feet corresponds to the energy of 10 knots excess energy. So this corresponds to 30 knots equal 1000 feet higher aircraft. Then the magic speed, the third rule, 220 knots, you have a vertical speed of 1000 feet, and the decreases in vertical speed is 300 feet for each step of configuration. Flap 1 and flap 5 speed brake, and the landing gear is 3 gears, so you will remember it's 3 times, so it's 900 feet per minute total. Last but not least, do not use the VNAV path if you are not on that specific correct energy profile. So only use the VNAV when you are on the correct energy profile. Otherwise, you have to act in order to recover your profile.
Paolo's Pilot Lounge. Like and subscribe now.
We now have to answer the last objective of the day is what can I do when the VNAV is not available? Now, when is the VNAV not available? Well, one of the cases we saw it when we are significantly lower than the profile, and the use of VNAV with the 1000 feet per minute logic of descent will still bring the aircraft in a too low position. So that is a case where VNAV is not available. It's not a good idea to use VNAV and bring the aircraft to a low altitude leveled flight. You are rather looking for a continuous descent. The other situation is when you are high, or I would say very high on profile, and updating the profile still can't produce a profile, a correct profile or an energy profile where you find yourself on profile. So you have inserted even at 330 knots descent on the FMS, still you find yourself high on profile. The other case is where the FMC is inoperative. Another case could be once you are vectored significantly far out from the lateral navigation. In the previous example that we did in the beginning of the arrival in Ciampino, where the air traffic control was vectoring, in fact, that was one of the problems, is that when you are under vectoring, you don't know what's the plan of the ATC, and sometimes you get vectors significantly farther out than the standard arrival, meaning that you now have to run a completely different mileage, and maybe you get yourself too low, or it's significantly shorter, so you find yourself very high. So using of the VNAV when you are significantly farther away from the lateral navigation becomes quite inappropriate, so you can't really use the FMC calculated profile if you don't know what's going to be the lateral navigation profile. And finally, there might be any other condition where the VNAV is unusable or unreasonable. What could be? Well, for example, you have a number of arrivals where the minimum and route altitude are very high. So those arrivals are designed for a protracted arrival in the terminal area, maybe a design for procedure 10s. But then it turns out that the air traffic control as lower minimum vector altitude may actually vector you for a straight-in approach. Now, when you load the procedure in the FMS, of course you can't load the procedure using the assumption that you will descend below the published altitude. Now, here again, it comes to company policies. Some companies or some captains will find totally reasonable and acceptable that you insert in the FMS a very low altitude, or even you cancel the altitude restriction of the arrival in order to have a correctly calculated VNAV profile. This might be reasonable, but personally I don't quite like it, because the policy is normally to use the vertical navigation, so the FMS for vertical navigation. By doing so, we basically insert or program the FMS in order to descend below a minima. And I don't think it's a good airmanship to program the FMS to descend below a minima. I would rather prefer seeing my first officer programming the FMS with all the minima applicable and having the FMS eventually in VNAV respecting all those minimas. But very often, as I say, those minimas happen to be quite high because of terrain, because of ITC, airspace organization, and what happens is that the VNAV actually is unusable because you actually want to be lower than that profile, knowing that most likely you will receive a vectoring that will actually bring you in a lower altitude than that minima published on the standard arrival route. So on these slides, here say we are on profile, the VNAV has been correctly calculated, but I can't use VNAV. Well, I don't see really the reason why you couldn't use VNAV. But if you want, you might decide not to use the VNAV. Simply follow the VNAV profile by using level change, I would say is the most appropriate selection, or if you prefer, using vertical speed, using a vertical mode that basically overlay the VNAV profile, and you actually still use the FMS to manage your descent, but you're actually managing the descent in level change. Of course, remember to decelerate at the same point where the FMC has calculated that deceleration point. Now, in the case you find yourself high on this profile, you can reason exactly the same way that the VNAV is doing. What is VNAV doing when he's high on profile? Well, just dive down like crazy and go grab that profile. So basically, that's what happens. If you find yourself high on a VNAV profile, but simply increase the speed, dive down in order to regain this profile. Below level 100, you won't have this facility because your speed is restricted to 250 knots. So you will probably have to use configuration in order to regain this profile. Once you are below level 100, we said you cannot use the facility of increasing the speed, and therefore the best solution is to use the drag. And we have seen how to use the drag. So basically what you can do in this case is to set the vertical speed that you need, so rejoin the vertical profile using the vertical speed, ensuring that the aircraft is getting back on the vertical speed, and you just play the game of controlling the speed by using configuration. Now again, you have to use your automation smartly, because if you are descending in VS, vertical speed, don't select speed 220 knots. We say this is the magic speed, yes, but don't select speed 220 knots, because if you select vertical speed and 220 knots speed, the auto thrust is going to be start moving the thrust levers in order to maintain the speed. You don't want the thrust to add energy in the system if you find yourself high. So in this case, what you do, you set the vertical speed that you need to get back on profile at the correct point, at the point I would say the beginning of the deceleration. Now, once you selected the vertical speed, you see what vertical speed you have selected. And by knowing the performance of your aircraft, as we said, it is 1,000 feet, basically level change to 20 knots. You realize that you need 1,600 feet, well, you would probably need flap 5, because we said flap 1 is 300 feet, flap 5 is another 300 feet. You need 1900, well, you might decide whether to go gear down, or you might decide whether to use flap 5 plus speed brakes, okay? So basically, one solution is to select the vertical speed. Now, consider that when you select vertical speed, you have to manage your automation correctly. If you select vertical speed minus 1600 feet per minute and you go flap 5 and you select speed 220, the auto throttle is going to be moving up and down in order to maintain 220 knots. Probably you're not going to need any thrust, but if for a moment, because of the fluctuation of the speed, you actually have a speed decreasing, you start giving thrust and adding energy to a system that does not need an additional energy. So the best technique to use in this case is to go vertical speed, bring back the speed to the maneuvering speed, so selecting flap 5 probably 160 knots, okay? So you bring back selected speed 160 knots, you use vertical speed in order to ensure that you get back on profile. And obviously, by knowing the performance of the aircraft, you will know that that vertical speed is reasonable or not. So if you have to select something like 1500 feet per minute in order to get back on profile, that's a reasonable selection if you are flaps 5 and the aircraft is already at 220 knots. It's an unreasonable selection if the aircraft is in clean configuration, because this is going to bring the aircraft in accelerating. If you find yourself in the need of selecting, for example, 2500 feet per minute, which is a massive vertical speed, well, that selection will be reasonable if you flaps 5 gear down. So yes, you can use this technique of vertical speed. You have to be cautious, as I say, to match the speed with the selected configuration and let the aircraft descend, ensuring you get on profile. If you want to be a bit more on the safe side, or I would say taking a bit less risk for what concerns the speed, you could use the level change. So you stay level change 220 knots, you go flap 5, you should expect a vertical speed of 1600 feet per minute. This will probably bring you below the profile. Once you're below the profile, then you start using vertical speed to reduce your speed. Even if the VNAV profile is unusable, the FMS gives us a very useful additional tool to calculate our descent profile. This tool is extremely useful once you start being in short final. Now, the problem of all those tools is that this requires experience, this requires practice. And I see that there's a number of pilots that never use these tools. Now, I'm not saying that you should use it on every flight. What I'm saying is that this is a tool which is available on your aircraft, and it would be a shame if you don't use it. If you start using it, of course, it takes practice. And the biggest mistake in using those tools is to mixing. So, for example, mixing the use of the VNAV profile with this vertical bearing tool. Don't mix it, because those tools are completely different. As we have seen on the VNAV profile is a profile that includes the deceleration of the aircraft, so the ramps of deceleration for the approach. This vertical bearing does not include at all any deceleration. Actually, does not include any LNAV. So in the case I was mentioning before, so the case where you are significantly far out of the LNAV and the VNAV start to be not really usable, well, this tool of the FMS still makes the FMS a very good friend of yours, very useful to determine your rate of descent. So first of all, we have to say that this waypoint altitude is not programming the FMS. In fact, if you try to set whatever point, whatever altitude in your descent page, you will see that there's no need to execute, because you are not changing anything at all in the FMC programming. So you are not changing the VNAV profile, you are not changing anything in the FMS. Those two lines, waypoint altitude and vertical bearing information, are calculation of information only. It will be populated with the next restriction altitude or waypoint restriction altitude, but you might program with whatever point you might wish. So it might be a useful information to put the final approach fix if you're sure that the ATC is gonna vector you close to the final approach fix. Obviously, if the ATC vectors you to 4 miles final, choose a closer point. But once you have programmed this point, this vertical bearing will give you a calculation of the angle from your current position to the point in a straight line, is not looking at the LNAV part. So this has nothing to do with the FMC programming. It's a pure calculation of the angle that goes from your aircraft to the point. It doesn't even include the radius of turn. So if you're coming in, for example, from 180 degrees intercept, so you have to do a procedure turn to do the final. Well, this thing doesn't calculate the procedure turn. Thinks that you are an helicopter, reach the point and then turn by 180 degrees straight away. Or if you're coming on base to final, it will not calculate the radius of turn. So this is a bare information, but because it's a pure information, not elaborated by LNAV, as I said, in the cases where the LNAV or the VNAV is not usable because, for example, you're out of the LNAV or the LNAV is incorrectly programmed, well, this will give you a significant help. How does it work? So we insert the point we're interested. Here in this case, I inserted uniform Roma Bravo NDB, which actually is LOCRI point, and I said I want to be there at 3,000 feet. Basically, I'm saying to the computer, I want to be at the final approach fix at the final approach altitude, which makes totally sense. As a response, the FMS will calculate for me the vertical bearing. This vertical bearing doesn't take into account any LNAV programmed route, so we can modify the FMC as I want. But all I get is the current flight path angle, so it means, you see, it was 0, so it means that this picture has been taken a moment where I was in level flight and the air traffic control was not giving us any descent. The vertical bearing is 3.3, so it means that I start to be slightly high because we say the inclined configuration of the 737 descend 2.8 degrees. So here I start having 0.5 degrees of error. So it means that I will have to rush a little bit in the descent as soon as I get clear from the descent. And you see that the vertical speed is a vertical speed calculated for my current ground speed. So given my current ground speed, I should be descending with 1,448 feet per minute in order to reach URB NDB exactly at 3,000 feet. Now, how to use this tool? Well, it's very simple. You have always to do more. Remember this. It's always worse than what it tells you. So if you are, like in this case, above the profile, and we are above the profile because 3.3 degrees is above the 2.8 degrees of clean descent, it means that as soon as the air traffic controls clears me for the descent, I will have to develop a significant rate of descent. How much? More than 1,448. So for example, 1,600 feet will be more than enough. So I could choose, as I said, either to select level change, 220 knots, it's 1,000 feet per minute, flap 1, 1,300, flap 5, 1,600, here we go, I got correct rate of descent to get back on profile. I could do this choice, or I could do the choice of selecting vertical speed, something around 1,500, 1,600 feet per minute, and using the configuration like flaps 1 and speed brake as much as is needed in order to control the speed. In this specific case, I wouldn't recommend to use speed brakes and flaps because it is not recommended by Boeing. So I would rather select the flaps. But basically, looking at this vertical speed indication, I might get understanding of what is the required vertical speed. Now, why more? Because I want to intercept the 3 degrees final segment before reaching the FAF. So I want to be on profile before reaching the FAF. Also because if I go level change to 120 knots and I intercept the profile exactly at LOCRI, well, I am on the ILS, but I find myself at 220 knots with flap 5, which is fairly fast. So I have to consider also the necessity of decelerating. So basically, yeah, I would probably use flap 5, having the option of having speed brakes in case I find myself very fast. Use level change in this case should give me a rate of descent that goes between 1,600 and 1,700, which is in excess of 1,448. So I expect to get on profile before the final approach fix, possibly as I said before, because the speed is drag, possibly what I'm going to do is that actually keeping 220 knots and descend below the glide slope and intercept the glide slope from below. So I will keep 220 knots as long as possible. Again, efficiency. This make flight time shorter, economizing fuel, and this make me have a less efficient wing, giving me a higher loss of altitude. And when I am approaching the platform altitude of 3,000 feet, then I will probably go vertical speed, wheel back the speed to match the speed of the current flap setting, flap 5, and let the speed decay, probably selecting a vertical speed of 100, 200 feet per minute, let the speed decay, arm approach, intercepting the glide slope from below. And that would be a very nice intercept of glide slope from below. So you basically converted a situation where you were above the glide to a situation where you are below the glide, and the speed is getting back in control. Now you have other tools to control the speed if you find yourself fast in final within the 10 nautical miles. So there are tricks to control the speed. There aren't tricks to control the altitude. You must be at the correct altitude. So don't keep yourself high in the approach. Be aggressive in correcting the profile between 20 and 10 nautical miles. Make sure you are on profile 10 nautical miles. Now, if needed, you will be aggressive in correcting the speed. In these slides, again, we discussed this concept. So here we are again within the 20 nautical miles. I'm high on profile. I'm not sure if and how I'm going to be able to recover the profile. Why this could happen? Again, because I'm vectored, and when I'm vectored, I can only see the decel point when I update the FMS. So it's a good practice to keep the FMS updated, but it's not always possible. And sometimes it happens that I update the FMS and turns out the decel point is behind me. So I might see myself on profile, like it is the aircraft in this example. I am on the vertical profile, but again, I'm not on the energy profile because my aircraft is far much faster than what it should be during this deceleration ramp. And at the end of this deceleration ramp, there is what I called before the mystery point. So the point where the deceleration ramp reached the 3 degrees final descent. Why this mystery point is so important? Well, simply because if I show up at that point in clean configuration, I will lose control of the speed. I will find myself too fast. So it's very important that I understand in which ramp, in which phase of the FMS am I. Because if I have to fly, for example, a no-precision approach using VNAV, well, finding myself on the deceleration ramp is a very good thing because my speed is going to be bleeding off. But if I am at the point where the aircraft was supposed to be at 200 knots, and I find myself at 250 knots, although the speed looks like descending, it's not descending fast enough. And therefore, I have to configure early. Now, if I see that the flight path angle from the descent page is changing from this 0.2, 0.5 degrees of the deceleration ramp to 3 degrees, now I must be very cautious because the aircraft is now in the final. And if I find myself still very fast, like 230 knots clean configuration, I've been bleeding off speed nicely, but now the aircraft started descent because it is in the final segment, and that final segment was calculated for 180 knots. Now, if I find myself that fast, the only solution to solve the problem is to go gear down and add an enormous amount of drag to the flight in order to bleed off the excess speed that I have at the beginning of this 3 degrees descent. So that's why I pay so much attention to this mystery point. But as I said, would it be an ILS? Would it be a non-precision approach flown with VNAV? The absolute priority, once you are within 20 nautical miles, is to bring the aircraft back on the correct profile. What you want is to bring the aircraft back on correct profile, and then once you are on profile, you eventually act aggressively to fix the speed. In these slides, this could be the example where I said you are unsure that you're going to be able to recover the profile. You see, in the situation where I am in an angle of 3.6 degrees, and the required vertical speed is 1,900 feet. and I'm actually descending in clean configuration at 2.6 degrees. So in this case, I have to significantly increase the drag. So here, the most appropriate solution will be to go flat 5, keep 220 knots, and try to descend as much as possible. Because I'm something like 20 miles out, it might be inappropriate to go gear down 20 miles out because I add an enormous amount of drag, and then I'm going to need thrust later on. But I must be ready to consider going gear down early, because as we can see, with 1,600 feet, I still keep myself high on profile. So maybe in this case, flat 5 and speed brake could be appropriate. Or maybe once I start being like even 40 miles out, I could decide to go gear down. So I have to take a decision. If the decision is an early gear down, probably flat 1 is enough. I let the aircraft get very high in profile. Then I go gear down, and with the level change in the gear down, I'm going to develop a rate of descent which is at least 2,300, 2,400 feet per minute. I'm going to descend with 220 knots, intercept the glide slope. Again, same as before, I'm going to descend below the glide slope, let the glide slope go above, and then select 200 feet per minute and intercept the glide slope from below. So that could be the plan. But again, here it wouldn't be that easy playing around with the gear, because, as I say, the gear will give me an enormous amount of drag. But there is a rule of thumb for the usage of gear as well. We're going to come to this in a moment. And as I said, once you're on profile, do not lose the profile. Keep using the drag device to control the speed. What is the drag devices to control the speed on short final? So let's try to build up some rule of thumbs for the, let's say, within 10 nautical miles. So we said 20 nautical miles out, I am very aggressive on the profile. I want my aircraft to get back on profile. I don't want to end up on the approach, crossing the final approach fix, being high. That is incorrect in terms of IFR procedures, and that is intercepting the glide slope from above or intercepting the vertical profile from above is, as a matter of fact, statistically speaking, a dangerous maneuver. It increases significantly the chances of accident. So what I want to do on all approaches is to bring my aircraft below the profile, even if this costs to me having a high speed. Okay, I want to bring the aircraft below the profile and intercepting the profile from below. But now this is done, saying that I achieved this result. So I achieved the result of bringing the aircraft on profile, but I find myself fast and final. So on final approach, normally at the very least, okay, some companies actually has it as an SOP, is to go gear down and flat 15 at 4 miles. I would say that is very tight, okay? That will bring the aircraft stable at more or less 500 feet. You can't be stable at 1,000 feet. So yes, there are some companies that has this SOP. I would say it's a tight SOP. I would rather say I would like to go gear down flat 15 at 5 nautical miles at the very least. But in all cases, it is demonstrated that you can go gear down flat 15 on a 737 at 4 nautical miles if your speed is correct. So you are on the correct speed. At 4 nautical miles, you go gear down flat 15, and it has been demonstrated that you can land the aircraft by being stable by 500 feet of gel. You normally get the stability around 700 feet. My recommendation is to have it at least at 5 nautical miles, the gear down flat 15. The ideal profile, the profile we say the objective of the descent, that ideal profile, would see you basically intercepting the glide slope with flat 5, and having the aircraft descending with idle thrust from the intersection of the glide slope at more or less 10 nautical miles until this hypothetical 5 or 4 nautical miles point. During this descent on the glide slope at 3 degrees with flat 5, the aircraft will slowly lose the speed, because we said with flat 5 you're a bit more draggy than what is needed to maintain speed. So basically with flat 5 on the ILS, the speed is gonna bleed off very, very slowly. I would say probably something around 10 knots every 3 nautical miles would be a good number. And it's a number to keep in mind. So normally that is the ideal deceleration during the ILS. Here you have a picture. The ILS is being intercepted, and that's more or less the rate of deceleration that the aircraft has. You see, I find myself at 3,000 feet on the glide, coming on lock, the speed is 190, decreasing very slowly. Most likely in this picture I will be able to go gear down at 4 nautical miles if we are VMC condition, and land basically being established just at 500 feet AGL. But what if I'm faster? What if I have to bleed off speed because I found myself high, I've been very aggressive with profile, descended below profile, intercepted profile from below, everything perfect, but now I need to fix the speed? Well, the rule of thumb on speed brake and flaps is very easy. If I select flap 10, this will give me normally higher selection. Depending on the 737 model, this could not happen. So the flap 10 could be eventually totally useless. Depending on the model of 737, on the NG actually the slat will go to fully extended, and this full extended slat at a higher speed will give you a higher drag. So you could decide to select flaps 10, or you could decide to use the speed brake during the final descent. Any of those selection will correspond to a more or less a loss of 10 knots every 3 nautical miles. It's an easy number, you know. You remember this 10 and 3 is coming back often because we said 10 knots split off is 1 nautical miles, 1,000 feet, 3 nautical miles, you know. So it's an easy number to remember that if I use speed brake, or if I go flaps 10 on an NG with a full slat extension, well, at this point I will lose an additional 10 knots every 3 nautical miles. My recommendation again is not to use speed brakes and flap, but to go flaps 10. Why this? Because if you're coming from a slightly high approach, probably you're very busy. You have limited capacity, and extending the brake just increase the workload. You cannot go flap 15 and a speed brake extended. And there's been many cases of pilot mistakenly leaving the speed brake out in flap 15. But why using the speed brakes in final approach? You have to land. The configuration you need is speed brake actually stowed and armed. So leave the speed brake down and go with flaps. You need to extend the flap. So if you go flaps 10, you actually do part of the job. If you go speed brake flap 5, you're actually overloading yourself, because now you have to do an additional item, which is stow the speed brake and configure the aircraft. If we need more deceleration than this, we can use the landing gear. You remember the landing gear, we say, is a huge amount of drag, 3 times the flaps. Now the rule of thumb for the landing gear, again, 3 times the flaps. So if flap 10 will give you a deceleration of 10 knots every 3, well, gear down will give you a deceleration of 10 knots every 1. 3 times more the deceleration. So again, an easy number to remember. So basically, if I go gear down, I will bleed off 10 knots every nautical miles on the 3 degrees glide slope. Meaning that if we say that the latest point to go gear down flap 15 in VMC condition is 4 nautical miles, so I want to be at 4 nautical miles at 160, maybe even 170 knots, okay? I really want to make it fast. This means that if you need to bleed off speed in short final, well, the gear might really help you. So you see that here in this scale, in black, we got the distance to go and the speed of the aircraft, which the distance to go, say in the ideal profile, we show up at 200 knots, basically 10 miles final. We bleed off something like 10 knots every 3 miles, meaning that I'll find myself more or less 190 knots and 9 miles, 188, and more or less 6 miles, 160 miles. Actually, there's a rule of thumb that says, well, look at the DME distance, and the DME distance, the digit of the DME distance should be the second digit of your speed. So 6 miles 160, 7 miles 170, and so on. Well, I don't really like this rule of thumb because it would be a bit too fast, but at the end it's not that wrong, okay? Now, if we take the gear, you remember that we say the gear is 3 times more drag than the flaps. So if the flap was giving you a deceleration of 10 knots every 3 nautical miles, by going gear down, you obtain a deceleration of 10 knots every 1 nautical mile. So in red, we have here a scale of the maximum deceleration we can obtain by using the gear down. So if I find myself fast in final, you see at 4 nautical miles, I could be even 170 knots with gear down. I still gonna land the aircraft stable at 500 feet. which means because I bleed off 10 knots every mile, now I could be 5 nautical miles at 180 knots, which is really fast. 6 nautical miles 190, 7 nautical miles 200 knots, 8 to 10, basically I can show up at 10 nautical miles at 230 knots. So as a matter of fact, if you show up 10 nautical miles on a 3 degrees glide, 230 knots, which is extremely fast, so I'm not saying that you have to do, don't misunderstand me, that is absolutely poor technique, and this pulls threads for the high energy approaches, especially if you have tailwind. But in calm winds and in a theoretical way, and I would say even safe, because the number I'm giving you are actually safe number. If you find out that you screw up your descent profile, but you are on the vertical profile, you intercepted the vertical profile from below, so vertically speaking your position is correct at 10 nautical miles, but now your speed is completely all over the place, you find yourself 10 nautical miles, 230 knots, by going gear down you lose 10 knots per nautical mile, and you will see that actually it works. You will be losing 10 knots per nautical miles, if not even more. I tell you, it happened to me a couple of times. We were a bit like, that's very fast, okay? You're not really relaxed looking at the speed, 230, 10 nautical miles in final. But, as I said, the gear is a very effective drag device. So basically, by using the gear and increasing the configuration, this ensures to you have good deceleration. This is a tool to control the speed once you are within the 10 nautical miles and you are on the profile. It will be a mistake to, for example, attempting to control the speed before controlling the profile, finding yourself high on profile. There are some companies that has SOP and they accept their pilots to intercept the final approach segment from above after the final approach fix. That is technically incorrect in IFR procedure. Looking at the IFR procedures, you have to respect the final approach fix. As I said, that is technically incorrect. Now, if the company has an approved SOP, then of course you can use it. But I would say in all cases it's not the best practice to intercept a glide slope or a final approach descent from above.
Paolo's Pilot Lounge. Like and subscribe now.
Now, in the other case, where the aircraft is extremely below the profile, again, I can use the vertical bearing page in a very effective way, because in this case, I will go in the vertical bearing page and I will see that the aircraft is giving me a vertical bearing, for example, of 400 feet per minute. And I know very well that my aircraft is descending level change to 1000 feet per minute. If the system tell me that to reach the final approach fix, I need to fly 400 feet per minute, remember what I said before, you have to consider that is always worst. So before we were high, the FMC told me 1500, I have always to select a higher vertical speed, 1600, 900, something a significantly higher vertical speed. Now the FMC tell me a very shallow vertical speed, 400 feet per minute, I have to select a much shallower vertical speed in order to make a continuous descent. So if the FMC says 400, I will select vertical speed 200 feet per minute. Of course, I keep flying my economy speed. There's no point in decelerating, absolutely no point in configuring if I am below the profile. So just keep flying that shallow rate of descent and intercept the vertical profile from below. Why selecting less? Because if I select exactly 400, the threat is that I actually level off a few seconds before the final approach fix, and I have to do a very small level of flight segment. I don't want to do that level of flight segment. I want to do a smooth, continuous, nice continuous descent until intercepting the 3 degrees from below. This will give me a much more stable approach. Now, of course, if I'm flying 250 knots, I have to consider the deceleration as well. Now, the deceleration in level flight, we said, is 10 knots every nautical mile. If you are descending 200 feet per minute, I tell you, there's not going to be much difference from the deceleration. So basically, you have to consider that once you're more or less 5 nautical miles from the final approach fix, 250 knots, you might start decelerating to the up speed. Once you're approaching the up speed, you're going to go flap 1, flap 5, start descending with the glide slope or with the final approach segment. Well, with this, we concluded, we covered all the aims of our today course, whose objective was to discuss the ideal descent profile and how to manage the aircraft energy during the descent. Let's take now some little bit of example and practical cases, okay? In this case, we see the air traffic control has authorized me for a route. The route was basically direct to the final approach fix. So of course, if the air traffic control give you this very good news, you're clear to fly direct to the final approach fix, you're more than happy to do that, and you fly direct to the final approach fix, you have to load that route in the FMS, no problem. But after loading this route in the FMS, you can see that this is what I obtained on my FMS. And the question is the FMC usable? Is this VNAV correct? Now, the lateral navigation is correct, and I actually have to use this lateral navigation because that's what the air traffic controls has cleared me to do, to fly to the point called GTOD, direct to the 8.3 nautical miles final in this case, which is the direct to the final approach fix. But while I have to laterally do this, what happens is that in the specific coding of the FMS, now I get a problem with the VNAV, so the VNAV becomes unusable. In fact, look on the right, I now find myself having 53 nautical miles of glide path of 3 degrees, meaning that the FMC is constructing a glide path 3 degrees starting from the runway 8.1 nautical miles, actually to the 8.3 DME from Romeo Oscar Mike VOR, which today is Romeo Mike Charlie, and from that point it continues on a 3 degrees glide for a total of 53 nautical miles. So basically the FMS wants me to fly or to intercept the ILS 3 degrees from 53 nautical miles. So we have lost that deceleration ramp, and you remember what we said, on 3 degrees the aircraft accelerates. So this is a case where you have to be very cautious and realize that the FMC is unusable. You don't want to be on that diamond, on the vertical diamond of the VNAV path, because the VNAV path is unusable. But if you're doing your calculation altitude by 3 plus deceleration correctly, you will easily spot the, I would say, miscoding of the FMS. Although it's not a miscoding, you have to use the FMS in this way. But you will spot the problem and realize that the FMC in the specific case is not available. What to do in this case? Well, I would say, for example, the vertical bearing, well, in this case becomes a very useful tool. So I would switch in using the vertical bearing and keep backing up my calculation with the altitude times 3 plus deceleration. In this example, we have the FMC this time is correctly coded, but if you look at the speeds, the problem is at the speed with 157 knots at 8 miles final, especially in Rome. The air traffic control is most likely going to be complaining. Standard speed is through the in final is 160 for category Charlie, but here you are 8 mile finals, which is more or less the position of the base, so the air traffic control would expect at the very least 180 knots. So having programmed the FMS like this is not completely wrong, but it is true that if you don't expect to do a fully stabilized approach, this FMC coding will make you to be below the expected profile if you then respect the standard air traffic control speeds. In this other example, I'm asking you, am I high or am I low? What happens is that the pilot is flying in level change 225 knots, and the FMC has been programmed for a profile of 245 knots, and the diamond is centered. So am I low on profile? Am I correct on profile? As we say, the profile is an energy profile. So the fact that the diamond is centered does not mean that we are on the correct profile. So here the answer is pretty simple, because you see that just 20 knots below I'm vertically, so potential energy is correct, but the kinetic energy is incorrect and 20 knots below. By being 20 knots below, my wing is more efficient, So basically, it's not a big deal flying this profile, I would say, although the deceleration ramp has been calculated from 245 knots to the flap extension, and now I find myself from 225 knots to the flap extension. Because the wing is more efficient, I will maybe recover a few knots. So maybe at the beginning of the deceleration ramp, I could find myself like 230 knots instead of 225. But as a matter of fact, this profile is incorrect because my energy is 20 knots lower. So basically, if I obtain a shortcut of 2 nautical miles, I will actually find myself on the correct profile. In the second example, the pilot is descending in level change 275 knots. We are on the vertical profile for the potential energy, so the diamond of the VNAV is centered, and the FMC program speed is 245 knots. So here again there is a problem. Well, are we high or low? It's obvious, potential energy we're correct. Kinetic energy we're 30 knots faster. 30 knots faster equates 1000 feet. So we are 1000 feet high or 30 knots faster or 3 nautical miles. If the ATC gave me a longer route by 3 nautical miles, by taking 3 more nautical miles, I actually find myself on the correct vertical profile. So how could I sort out this problem? Well, it depends from the altitude. If I am above level 100, it might be a good idea just to program a higher speed in the FMS, obviously not 275. Probably going to need to program something like 270. But you remember what we say, the deceleration ramp at level 100 is going to get longer and longer the faster I fly. So it really depends from the altitude. If I am at level 150, maybe 275 is a good speed, maybe 280 is a good speed. If I'm very, very high, then, well, the length of the deceleration ramp is kind of unaffecting the total length of descent. So if I'm level 300, probably by selecting a descent speed of 255, it's going to sort out the problem. If I'm at level 200, probably selecting a speed of 270 could be a good guess. Now, once the speed is 270, I'm going to go level change 270, verify that the diamond is center. Once the diamond is center, I will engage back VNAV, and now the VNAV has been calculated for a speed of 270. So I am back on the VNAV profile. In this specific case, I am flying at 320 knots, level change, and I find myself 1,200 feet below the profile. So the FMC has been programmed with 245 knots. I find myself 1,200 feet below the profile, and the actual speed is 320. So now we have to do a little bit of math there, okay? In terms of potential energy, it's obvious we are 1,200 feet below. In terms of kinetic energy, we are something, if you want to round up to 50, or something like 70 knots faster, okay? And you remember what we said, that 1 knot equates 1 nautical mile. So 30 knots equate 1,000 feet. 3 nautical miles, 1,000 feet. Because I'm 70 knots faster, what happens is that I am something like 2,300 feet faster, higher energy than what is required. So in terms of potential energy, I'm just 1,200 feet below. In terms of kinetic energy, I can convert these 70 knots into potential energy. And if I do so, these 70 knots equate 2,300 feet. So the result is that in total, I am 1,200 feet high. Meaning that even if I'm below the profile, and I go level change now, 245 knots, by the moment I reach 245 knots, I'm probably gonna find myself 1,200 feet high on the potential energy profile, on the FMC VNAV profile. So solutions, well, I can't keep descending at this high speed and wait until the vertical speed tells me that I am something like 2,300 feet below profile. Maybe a bit less, 2,000 feet, because by the time I actually decelerate, I'm gonna waste a little bit more energy. So that could be a solution, very easy solution. You know, I just bleed off as much altitude as possible by keeping 320 knots. Once I am 2,200 feet below, I just bring back the speed to 245 knots, and I should discover that I am more or less on profile. That could be a solution. Other solution, update the FMS. So I update the speed for the FMC profile. Again, I could select 280 knots, 270, and try to get this profile. Now, of course, here experience plays the game again. Because say that, for example, I am in descent toward London and I find myself in this situation, I would greatly prefer to use the level change 320 knots and fix the problem straight away. Because here I am high, but okay, just 1,000 feet, but I am high and I want to recover this profile. Very often what happens is that as you get closer to the terminal maneuvering area, the air traffic control is going to start assigning you speed restrictions. So if I say, okay, a good idea, 280 knots will sort out the problem, let's reprogram the FMC for 280 knots and 250 below level 100, and now I'm on profile and I'm happy and I go VNAV, spot on profile. Yes, it's not always the good solution. Because as I said, what could happen that now I find myself level 250, the air traffic control start assigned to me 260 knots, 240 knots, and now I find myself high. So by fixing the problem early, as I'm doing now, level change 320, descending much below the profile, and fixing the problem straight away, will allow me to go back to the speed of 245. Well, maybe I'm gonna descend for a longer time, but what happens is that very often when you start approaching the TME, you start approaching level 200, the air traffic control start giving you speed restriction. Well, that's more or less the problem, where anyway you were seeing those 2,000 feet below the profile and it was about time to reduce the speed. So you see, it's not always the best solution to use blindly the FMS. In some cases, the experience might dictate a different solution, and this would be an example where you are actually using the VNAV. So you are looking at the VNAV, but you are descending level change in order to recover the VNAV profile. In this example, well, that's the example we said before, the air traffic control is keeping me high, so they don't give me a descent. I have the FMC already programmed for a 320 knots descent, but they didn't give me any descent, so I started bleeding off the speed. I keep altitude constant and I bleed off the speed as much as possible in order to be on this 320 knots energy profile. So am I high or low? Well, let's do the calculation again. We have a profile of 320 knots energy profile. Actual speed is 220 knots, so we have 100 knots difference. 100 knots difference is 10 nautical miles, and 10 nautical miles correspond with the altitude by 3 to 3,000 feet. So if from 220 knots I now press level change and select 320 knots, in order to regain those 100 knots, I will lose the equivalent altitude of 3,000 feet. And at the moment, we only have 2,000 feet above profile. So basically, in this situation, I'm actually below the energy profile. Although I am, in terms of potential energy, 2,000 feet above, in terms of kinetic energy, I find myself in the equivalent of 3,000 feet below. So all I have to do, as soon as the ATC gave me the descent, is to go level change 320, and I will probably find myself even below those energy profiles. So if I really want to descend 320 knots, I will probably be in the need of adding thrust in order to stay on this calculated FMC profile. Let's take another example. And in this case, we are level change 270 knots. The air traffic control just told me maximum speed is 270 knots. What happens is that I find myself above the profile in terms of potential energy by 400 feet. The FMC profile has been calculated for 300 knots. So am I above or below the profile? Well, here I have to consider that I got 30 knots less. So 30 knots less equates, again, 30 knots is 3 times 1 nautical miles, equal 3 nautical miles total. 3 nautical miles equates 1,000 feet. So in terms of energy, I am 1,000 feet below the FMC profile. But in terms of potential energy, sorry, that was in terms of kinetic energy. In terms of kinetic energy, I have the equivalent of 1,000 feet less. In terms of potential energy, I find myself 400 feet above. So I find myself 600 feet below the energy profile, which is a good thing because the ATC just restricted my speed. So I won't be able to descend at 300 knots. Because the air traffic control restricted to 270 knots, now I find myself in the need of descending with a more efficient speed. So all I have to do here is to recalculate with the FMS a profile for 270 knots and see what is my actual position compared to this 270 knots profile. Again, depending on the altitude, depending on the length of the acceleration ramp, I could be above, I could be below the 270 knots profile, but as a matter of fact, because in total, at the moment, this 300 knots profile, I find myself 600 feet below, well, I expect with 270 knots, which is a more efficient profile, to find myself pretty much close on that profile. So probably with the new updated profile of 270 knots in the FMS, I'm gonna be pretty much close to the FMC profile. So another example here, my high or low, we're descending at level change 270 knots. The up speed, clean configuration. The FMC says 207 flap and 600 feet high. Well, there is a big trick there. Here, well, it's very difficult to say whether we're high or low, and the question is extremely difficult to say how high we are. But in terms of potential energy, we are at 600 feet higher. But in terms of kinetic energy, is extremely complex to determine. Because once we cross the 245 knots decel point, exactly at that point, the aircraft is supposed to be at 245 knots. But after I cross that point, the FMC will switch to active 207 flap and will stay on 207 flap until I actually extend the flaps. So for me, it's not really possible to see what is the current speed, or basically where am I exactly on the deceleration ramp from 245 to the flap extension to the flap 5 180 knots start of descent. So this ramp that goes from 245 to what I call the mystery point, I can't really see where we are. If we are in VNAV path without speed intervention, then yes, I can see what the speed is, because I will see 245 knots and I will see the speed bag automatically going back to the selected speed. However, the speed bag will never go below 207 if you don't select the flaps. So again, you can see, but not completely everything. So what am I saying is that if I find myself, as it is in this picture, 600 feet high, and level change 207 knots, I could be potentially in a fairly good position, because maybe I just crossed the deceleration point. So the FMS calculates that I should be at 245, I'm actually at 270, so basically I'm 40 knots less. 40 knots less is 1,200 feet, and I'm just 600 feet high. So I got 1,200 feet equivalent kinetic energy less, and I'm just 600 feet high. So basically I'm perfect for this approach. I'm even slightly low. So I just keep descending 207 clean configuration, and that's no problem. But this is if I just crossed the decel point. So I crossed that point where I knew that the FMS was calculating my speed being 245 knots. Now let's pretend that we've been vectored and we now received the final vector. The pilot monitoring has inserted that vectoring in the FMS. The FMS has recalculated the profile, and turns out the decel point is behind me. So I can't see where the decel point is. And now that is a big problem, because I am in level change, not in VNAV. So I can't see the automatic bug moving. And I don't know where are we on this deceleration ramp. We could be lucky and be just at the point where the deceleration ramp is 240 knots. Or I could be unlucky. I could be in the point of the deceleration ramp where the aircraft should be at 190 knots flap 5. And I'm still 207 knots, 600 feet high. And this 600 feet corresponds to 20 knots. So basically I'm 227 knots in terms of kinetic energy if I find myself exactly approaching the mystery point. Even worse, if I am approaching the mystery point 600 feet high, it's going to be nearly impossible to shoot the approach, because one thing is recovering this 600 feet during the deceleration ramp, but the aircraft is normally descending around 200, maximum 500 feet per minute. One thing is recovering the 600 feet once the FMS is on this 3 degrees. That's why I pay so much attention to this mystery point, because I want absolutely to make sure that I am on the VNAV profile, especially non-precision approach where I use LNAV and VNAV for final segment. I want to make sure absolutely that I am on the VNAV profile before reaching this mystery point, because it becomes nearly impossible to recover the VNAV profile once the FMC is on a 3 degrees descent. So for this reason, here the answer is extremely difficult, and basically is, I don't know, use extreme caution. But if you find yourself in this situation where the decel point is gone and you don't know where it is, just behind you, be very aggressive, bring the aircraft back onto profile. So in this case, I will probably go speed brake, level change 230 knots, or probably if I have the doubt that I'm even closer, I will go straight away flaps 5, level change 230 knots, make sure that the aircraft descend and intercept the VNAV. I want to be on the VNAV before the beginning of the final approach segment, of the beginning of those 3 degrees. And again, we have seen how to fix the problem. Even if you show up at 230 knots, 10 nautical miles, gear down straight away. Well, you came in very fast, gear down straight away should be able to fix the problem. Alright, ladies and gentlemen, with this we concluded all our aim of the day. We have seen some examples. We can make a final recap on the rule of thumbs we have learned. So we say the first one is programming the FMS, expecting the shortcut. Don't expect to fly the full arrival. We said experience play an extremely important role in the descent planning. If you don't know, put a DME on the field, keep yourself within a 3 degrees glide from the field, and this will make you safe. Now, if you have better experience of the destination, then you know how the air traffic controls handle the traffic, and you might better plan your descent. Another golden rule, not to use the FMS if the FMS is incorrectly programmed. We have seen several cases like respect of minimum en route altitudes, or direct routing that creates a 3 degrees glide which is way too long, as we saw in the example, or simply the aircraft being too low on profile. So the golden rule is, if you know that the FMS is unusable in terms of VNAV, don't use it. We have seen the use of the vertical bearing page and the rule of thumb concerning the deceleration of the aircraft. We said fly level change 220 knots, develop a vertical speed of at least 1,000 feet per minute. Every flap selection, flap 1, flap 5, or speed brakes will increase the rate by 300 feet each. And if you go gear down, you actually increase the rate by 900 feet, 3 times 300 feet. We have seen the rule of thumb on how to bleed off speed on final segment. So we said once we are within 20 nautical miles to 10 nautical miles, be very aggressive with profile. I want to be on the correct profile. Once you are within 10 nautical miles, be extremely aggressive with the speed. I want to be on the correct speed. And we have seen some rule of thumb, more or less, the loss of speed with flap 10 or speed brakes, more or less 10 nautical miles, 10 knots, sorry, each 3 nautical miles. But if you go gear down, you again multiply by 3. So if you go gear down, you lose 10 knots each nautical miles. We have seen that these allow you to do an approach at a very fast speed. We saw that even 230 knots, 10 nautical miles can be fixed if you managed to get on the correct profile at the beginning of the final approach segment. We then get into the discussion of the aircraft energy. Of course, the golden rule, altitude by 3 plus deceleration, that's, I would say, absolute survival rule for pilots. And then we discuss the aircraft energy, the equivalence of the kinetic energy with the potential energy, we said that 10 knots equates 1 nautical miles and 3 nautical miles equates 1,000 feet. So 30 knots are the same amount of energy of 1,000 feet and will allow you to fly without thrust for 3 nautical miles. We then saw what is the point where you should take action to correct, and we said 10%. Start thinking about doing something and fixing the problem. And finally, we have seen the usage of the vertical bearing. For example, for low situation, we say always go worst. So if the vertical bearing tells you you need 600 feet per minute, select less, 300 feet per minute. The vertical bearing tells you that you need 1,500 feet per minute, select more, 1,900 feet per minute. So we said that vertical bearing might be very useful in that little segment, the crucial segment within 20 nautical miles and 10 nautical miles. As a conclusion, ladies and gentlemen, thank you very much for your attention today. Of course, we have resumed a 2-day course, a 16-hour course in a relatively short video. I know that for the standard of the internet, this video once again is extremely long and boring. Thank you for your attention. I hope you will find this video useful for your line training. Would it be as a cadet? Would it be on a common grade? As I say, the purpose today was to pinpoint some key element. Remember that as a captain, especially for the common grade, the line train captains will be looking carefully on how you realize and manage the energy of your aircraft. That is a major reason of failure. As a first officer, you very often have the captain popping up and say, I think you should do something. Once you're sitting on the left, there's not going to be anyone telling you, I think you should be doing something. It's you, the man, saying, I think you should do something now. So you need to have the adequate amount of tool, and you certainly have with your experience this adequate amount of tool, but today we pinpoint the key elements in order to give you a more clear idea and a more, I would say, certainty about the aircraft ability and capability to manage the energy. Meaning to understand very early, even before crossing the final approach fix, if your aircraft is too high on energy or not. Taking a decision not to shoot the approach is a good decision, and normally it won't even require any explanation. If the air traffic controls vector you too high, too fast, you can just say we're too high or too fast for this approach, unable for the approach, and basically ask for a new vectoring. And that is a very simple solution, I would say. The last thing that a captain wants to do is to be in the need of giving explanation on why his aircraft was on a high energy status in terms of potential energy too high for the approach or kinetic energy too fast for the approach. Today we have seen all the tools. We said between 20 and 10 nautical miles to run, look at the vertical profile, so the potential energy within 10 nautical miles, look at the kinetic energy, and we have all the tools to manage the aircraft energy. So you might take an early decision or foreseen very easily if your aircraft is going to be able to shoot the approach or not, if your energy is too high or if it's fast but manageable. I would say it starts to be quite unreasonable that a captain allow his aircraft or his first officer to fly below 1,000 feet knowing that the aircraft energy status is too high for a proper approach. Don't put yourself in that situation. Anticipate your calculation early. Anticipate the high energy approaches. Don't put yourself in that position.